Hi, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. This time we are finally getting to the most massive, most compact, most bizarre objects in the universe, black holes. Black holes are the final triumph of gravity over all the matter or any matter. They're the end states of the cosmos, and they are the horizons into nothingness. So what's really interesting about them is everything. So let's see what they are. Back in 1783, a scientist and clergyman named John Michell looked at Newton's ideas of the nature of what gravity was, and he also looked at Newton's ideas concerning corpuscular light. We talked about that in an earlier lecture, the corpuscular nature of light that Newton came up with. Well, John Michell took that seriously and said, well, if light is made of particles, then it has to have energy in order to fly up out of something. So imagine that you actually toss something up, but it came back down. So if light's a particle, then presumably you could make something where the escape speed is greater than the speed of light. And since in 1783 they had a pretty good idea about what the speed of light was, then they could find. He stated in his speech at the Royal Society of London in November 1783 that if you took something that was the same mass and density of the sun, but made the sun 500 times bigger with the same density that currently is, then light could not exit from the sun. And that's really interesting. You could all light from such a body would be made to return to it by its own proper gravity, which is fascinating. So John Michell came up with the concept of what he called dark stars, which is a really cool way of talking. Then in 1796, Pierre-Simon de Laplace, who is one of the more famous mathematicians of the 18th century, and in fact one of the most famous mathematicians of history, discovered that mathematically there really actually could be stars whose gravitational field could be strong enough such that the escape speed would be the speed of light. The other was a consideration, but this is a mathematical proof. Then it took a long time before Carl Schwarzschild in December of 1915 looked at Einstein's equations of general relativity and actually made the first solution to Einstein's field equations. And the field equations describe the relationship between the curvature of space-time and the matter and energy embedded in that space-time. And so what he did is he said, okay, let's keep it really simple, make it spherically symmetric, make it non-rotating, make it static, and put that spherically symmetric matter in one place with nothing else left in the entire universe. And he created the way to measure space-time around such an object, the Schwarzschild solution to the Einstein field equations, which is shown in that little equation below. But what he did is he actually wrote this thing while he was serving in the German army in World War I. And he wrote to Einstein saying, sent a letter to him and sent his notes off to Einstein. And Einstein replied and said that he thought it was a wonderful treatise and a wonderful solution to it. And he presented it in Carl Schwarzschild's name at the Academy. So so that was an amazing thing that he was able to do, because Carl Schwarzschild died about a year later from a genetic disease that developed while he was on the front, not as a result of injuries at the front, but he died shortly thereafter. So his work lives on, and the name of the thing that we think of as black holes lives on there. Then about 20 years later, J.R. Oppenheimer and Hartland Schneider, who was a graduate student at the time, in 1939, described what would happen if a star exhausted all forms of nuclear fusion and then exceeded the neutron degeneracy pressure. And so I list that thing there, and they said, well, there would be nothing to hold it up. And so that would collapse down to an infinite singularity, a black hole. So that's where the original idea comes from, because Oppenheimer himself, just earlier that year, with a couple of others, actually figured out what the neutron degeneracy support could be for a neutron star. And then they posited, and Oppenheimer and Snyder then posited what would happen if nothing could support it. And so they found that it would actually free fall all the way to a singularity as nothing left in existence below it. All right, so let's see what we know about these kinds of objects. And if we compare, say, the Earth, and initially let's go back to our study of white dwarfs. White dwarfs are these insanely dense objects that are about the mass of the sun, or thereabouts, up to 1.44 solar masses, and they're about the size of the Earth. So the gravitational pull of a white dwarf is supported by degenerate electron gas pressure. Not normal, not a solid, it's not a solid, it is not a normal gas, it's a degenerate electron gas. So the neutrons and the neutrons and protons and nuclei are buzzing around just like normal, but the electrons are all stacked in their lowest possible energy states, and there's no way to compress the gas. So if you add more mass to a degenerate electron gas, the actual white dwarf gets smaller. So remember we said that a degenerate electron gas has a maximum mass of 1.44 solar masses, the Chandrasekhar limit, and that dictates whether or not a white dwarf can exist above that mass. However, in the throes of a huge explosion, a neutron star can be formed in a type 2 supernova, and that can exceed the Chandrasekhar limit and compress the electrons and protons together to form a neutron star. And the neutron star can be between, say, about one solar mass up to about 3 or so solar masses, and those things then support by neutron degeneracy. So the neutrons, well, we wouldn't really think of it so much as a gas, because when we studied neutron stars, we learned that, well, they're very odd things. They're not really we wouldn't think of them as a gas. They're harder than any possible solid, even though they behave in certain ways as a gas. Mostly they behave like a superfluid, and the states of matter of a neutron degenerate gas isn't really gaseous in a way. So, but in any event, it supports against the pull of gravity. So that's one pressure that can push back against gravity, is neutron degeneracy. However, if the star that creates a type 2 supernova is more massive than about 18 solar masses, then that would create a supernova that would create a core larger than about 2.5 or 3 solar masses, and neutron degeneracy would not be able to support that against that pressure, against that pull of gravity inside such a small thing that's only about 10 kilometers across. If it exceeds about 3 solar masses, it will collapse, and it will collapse down inside. Oppenheimer and Snyder found that there's nothing that would stop the collapse. Absolutely nothing is known to physics. And in fact, what's even weirder is that it is known that from general relativity that pressure itself is an energy density. And so as the pressure rises, the pressure itself contributes to the energy density and then further hastens the collapse. So even if there were another version of pressure, it would contribute to the collapse itself. So therefore, anything more massive than about 2.5 solar masses inside of a small radius, such as about 10 kilometers, there is nothing that can support it. The core of the star collapses to a singularity, and it becomes a black hole. So this is really interesting. It's got this kind of, what is a black hole? Well, it's not a hole so much as anything. Well, we're going to describe what these things are. But a black hole is actually we can think of that white ring that we see in this image as a surface. And that surface has a very special feature. And we're going to see what that surface is shortly. But first let's revisit the concept of escape speed. Remember, right in the beginning from 1783, people said, well, if something had the escape speed, the speed of light, then light couldn't leave. So let's look at what that means. Well, we can think of the kinetic energy, which is that 1/2 mv squared for some mass. The faster it's going, m, some mass, the v is the speed, then it gives you the kinetic energy of it. But if that's equal to the gravitational potential energy, we say, if it's just equal, the amount of kinetic energy of a particle is just equal to the gravitational potential energy of that particle, which is, say, the Earth, which is the capital M, times the mass, maybe it's like a gas particle or a rocket or anything, divided by the radius from the center of mass, or the distance between those two centers of mass. If we equate those two things and solve for the v, we get what's called the escape speed. And that is how fast an object must go such that its kinetic energy exceeds the gravitational potential energy, meaning how much energy it is by falling. And for the Earth, if you plug in for the mass of the Earth and the radius of the Earth, you get an escape speed of about 11 kilometers per second. So that's pretty fast. So if you want to escape the Earth and never fall back down, you get so much energy that you exceed the gravitational potential energy and never fall back, you've got to go 11 kilometers per second. That's really fast. The average person can run, the average really good athlete can run a 10 kilometer, or the average person can run a 10 kilometer road race in maybe an hour or so. Elite runners can run it in, say, 20, 25 minutes. But for the Earth, if you want to get away from it, you got to go 10 kilometers in 1 second. So that's about 11 kilometers in 1 second, which is the equivalent of going around the outer loop of Central Park in 1 second, which is really fast. So that's how fast you got to go in order to escape from the Earth. So let's see what happens if you shrank the Earth. So currently, if you went just 10 kilometers per second, you go up very, 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 very high, and eventually you'd fall back down. If you're going slower than 11 kilometers per second, you're going to fall back down eventually. But if you go faster than 11 kilometers per second, you will eventually you will escape from the Earth. Now, if you shrank the Earth, kept the Earth's mass the same, you just compressed it, and you pushed the Earth down 100 times smaller, so that it was 65 kilometers across, then the escape speed would be 110 kilometers per second, because it goes as the square root of the radius. But if we then said, fine, what do we got to do in order to make the escape speed 300,000 kilometers per second? And that means you got to shrink the Earth down to about 1/3 of an inch, or a few millimeters. That's really small, smaller than a centimeter, about the width of your pinky nail. So if you took the Earth, the entire Earth, which is over 12,000 kilometers across, and compressed it to smaller than your pinky nail, then the escape speed would be the speed of light. That's a pretty incredible compression ratio. And so what's going to do that? Well, a supernova can do that. So what is a black hole? It's the extreme ultimate object. The gravity, therefore, is so strong that nothing, not even light, can escape. And any infalling matter, something that falls into a black hole, gets totally torn apart by tidal forces that basically mean that the gravitational pull between, say, the top and bottom of something gets pulled apart. That's the tidal forces of it. And the escape speed escapes the speed of light. And it's a black hole because it's the surface of the black hole, whatever that is, we don't even know what that really means yet. But that surface, we're just going to say that for right now, if the escape speed is the speed of light, then light can't get out. So therefore it would be black. And it's a hole because, well, nothing goes faster than the speed of light, so therefore anything that goes in doesn't come out. So that's why it's a black hole. And let's talk about that surface for a little bit. It's a very odd thing. We're going to call that radius, that special radius, the Schwarzschild radius, which derives from Karl Schwarzschild's metric, the way you measure space and time near a spherically symmetric object. And we'll measure that to say that since light cannot escape a black hole, if it comes closer than a radius, that's called the Schwarzschild radius. And that if it gets inside that Schwarzschild radius, it will fall to the singularity no matter what. And so if we look at R sub s, which is the definition of the Schwarzschild radius, it's 2 times the gravitational constant times the mass of the object divided by the speed of light squared. So all you have to say is that, wow, you can take whatever mass it is. It doesn't matter what the mass is. It can be an Earth-sized mass. It can be a sun. It can be, say, 1,000,000 solar masses. Then you can derive what the Schwarzschild radius is. So something like the sun is about 3 kilometers across. So if you have a black hole that has the mass of 1 solar mass, the size of the Schwarzschild radius, the radius of the black hole, is 3 kilometers. And if you look at a white dwarf, the white dwarf has a radius of about the size of the Earth, which is about 6,000 kilometers. And if a neutron star is about 10 kilometers. So the size of a black hole is really not that much smaller than a neutron star. So neutron stars are just on the boundary of being, of compressing inside their Schwarzschild radii. That's why they're such extreme states of matter that we saw in the previous lecture. All right, so now let's take a look at what the relative sizes of a black hole are, and we're going to do it by a size scale comparison. So here's the size of the sun, and this is a beautiful image taken in visible light of the sun, actually an ultraviolet light of the sun, and we see a beautiful prominence from the sun reaching out. And I've put the Earth underneath the prominence for correct scaling, because remember the Earth is about 100 Earths can fit across the sun, so that's about right for the size of the Earth compared to the size of the sun. It's actually that pixel's a little too large because we need 100 to fit across there, and it seems like we get less than 100 if we use that one, so it's going to be a little smaller now. But let's zoom in anyway. And we see there's the size of the Earth with respect to this prominence, which is a typical large prominence on the sun. And now we zoom in onto the Earth and we go all the way down to, say, Florida. We look at Florida and we zoom into Florida and we keep zooming in and something is appearing and we're looking at a particular area in Florida and we zoom into that area and we find a black circle. The size of a black hole, the mass of the sun. So we take that entire thing of the sun and compress it down to this big, which is just about the size of Cape Canaveral Air Force Station, which is where they launch all of the rockets from. That's the launch pads you see around it. And there's the landing strip that the space shuttle used, as well as other planes and aircraft that come in for a landing. But all of those launch pads are the great launch pads for the Apollo missions, as well as the space shuttle and many other things. But if we look at the size of the black hole, it's really small. It's only a few kilometers across. That thing's small, you take all of the sun and compress it down to that. Now, of course, if you put it right next to the Cape Canaveral would no longer exist because it would be torn apart by the incredible tidal forces that would shred the Earth immediately. But that's just to give you a sense of scale. So now we're going to use a new word, a new definition. It's called the event horizon. The Schwarzschild radius defines what we mean by what's called the event horizon, and that event horizon surrounds the black hole's singularity. Anything occurring inside the event horizon, inside the Schwarzschild radius, is invisible to the outside universe because light can't get out from inside the Schwarzschild radius because it has to go faster than the speed of light to get out, so you can't. So no events happening inside the Schwarzschild radius can be seen. So this is an effective horizon. In fact, it is a horizon. Horizons are things you can't see over and around, right? That's kind of the definition of the horizon. Things are past the horizon, they are over the edge of the curvature of the Earth, so you can't see them. And that's what we mean by a horizon. And so the horizon is just the place where we cannot see anything from below there. Anything closer to the singularity than the Schwarzschild radius never leaves the black hole, can't come out, there's nothing it can do, nothing ever comes out, I don't care what anybody says, it's a lot of fun to say, you're going to find all sorts of silly speculation everywhere. It doesn't happen, that's the nature of an event horizon in a Schwarzschild radius. So that's what we call the event horizon. The event horizon is also the surface that black surface. It has a radius of the Schwarzschild radius. And that's not really a surface. There is nothing there. That's weird. No, we think of it as, oh, what's on the event horizon? Well, there is nothing on the event horizon. That's just the place from which light cannot escape. So it is black. There's nothing there. It's inside of there is the singularity, but we cannot see anything from there. No events can be seen from inside of there. And that surface is a mathematical construction, and it only exists because, well, you just can't see it. So that's what we call the event horizon. Gravity around black holes is insanely intense. However, if you're far from the black hole, let's say a one solar mass black hole, if the Earth was orbiting 1 astronomical unit away from a one solar mass black hole, the only difference would be, well, there might be some X-rays as stuff falls in, and it would be certainly there would be no sunlight, but we would orbit. The Earth would orbit that black hole. So the only effects that happen are when you're very close to the black hole, when the radius of your orbit is less than about 3 Schwarzschild radius, then there's no stable orbits, which is kind of funny to think. We can think of stable orbits getting very close to the sun, but once you're inside 3 times the Schwarzschild radius, there are no stable orbits and things just fall in. That's one of the strange things that occurs inside of the dynamics due to the Schwarzschild metric. So mass would definitely fall in, but at 1.5 times the Schwarzschild radius, or look at that disk there and just take half the radius and push it out again, and that's where that Einstein kind of golden ring is, that pinkish ring is around. is that photons or light would orbit in a circle, and they can't get away. So if light was orbiting there, it would be like this glow of light that simply can't leave. So if you happen to fall through that, you'd see a bright light as things hit you in the face. But you would never actually see anything escape from there. And so the photon, if a photon could go up and it could go down, mostly down, but inside 3 Schwarzschild radius, all normal matter falls straight in. All right. So why does this happen? And we're going to discuss some really very interesting concepts associated with black holes in just a little bit. But we talked about general relativity in a previous lecture in the series, and we discussed the concept of the equivalence principle. And the equivalence principle is Einstein's great insight into the nature of space and time. And he simply said that all physical laws are the same, no matter how the laboratories in which they are measured move with respect to each other. So if you're on the surface of the Earth, you're going to have the same physical laws as someone that's in a rocket, accelerating upwards at the same exact acceleration as someone standing on the surface of the Earth. So you can't tell whether you're in a boxed room on the surface of the Earth or in a rocket accelerating upwards at 1g acceleration. Likewise, there's no way to tell if you're floating freely in space in a box and falling towards the Earth freely in a box. There's no way to tell the difference between them. However, there are definite differences between these two things as seen from outside observers. And also in the bottom pair show freely falling. The others show not freely falling, but accelerated frames. In fact, you could even look at the one on the lower right as an accelerated frame as well, but it's freely falling with respect to the observer who's falling. The equivalence principle says that all physical laws are the same for all laboratories, and if you wish to understand how things are slightly different, then you simply must take into account the fact that there's curvature of space-time, which affects how you measure what you're seeing in someone else's laboratory. But inside your own laboratory, no matter where you are, you measure all the same physical laws. That's how that works. It leads to some very strange constructions. But let's just kind of put those words out here to really demonstrate what I mean. And the equivalence principle really means that everything, quantum mechanics, electrodynamics, mechanics, all sorts of things, thermodynamics, all of them are the same for all inertial observers, no matter what. If you're in free fall, or floating, or standing still, or moving with a uniform speed, or even falling in a uniform gravitational field, there's no way to tell any of these things apart using any known physical law. That's incredibly important, because that means that general relativity, which is a description of gravity, says that gravity itself is a fundamental interaction that's relative to the observer. So that's what we mean. It's not a physical law in of itself, like quantum mechanics or electrodynamics or thermodynamics. It is a fundamental interaction that's relative to what you're observing. So Newtonian gravity can then be said, okay, Newtonian gravity, like we talked, F equals gmm over r squared, right? Keep that old Newtonian gravity dance. And you can restate it not as a force. So now we think of it as not as a force due to gravity, but rather a curvature of space-time. So space-time is curved, and so therefore things fall according to the curvature of the space-time in which they exist. There's no force. Everything's just following the lay of the land. And so far, general relativity has survived extraordinarily stringent tests, and there's been amazing tests that we'll talk about when we talk about gravitational waves that even provide even greater tests for general relativity. And there are other tests as well that seem to say that so far, general relativity is the most correct description of gravity, because right now it has very testable predictions, and those tests and the predictions from those tests have been supported. So what's it like falling into a black hole? All right, let's pretend we got 2 astronauts, and there's one astronaut inside a rocket, and then that rocket, and her name is Jill, and she hangs out in the rocket, and her friend Jack is going to go fall down the hill. And so Jack gets out and gets in a separate little box in a spacesuit, And what he's going to do is he's going to fall towards the black hole. And he's got a laser, and the laser's blue, and he shoots it at Jill, and Jill says, okay, just hit the target. Don't hit my face with that thing. That's really irritating. So he then falls towards the black hole, shooting the laser in pulses. Every second he goes pulse, 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 pulse. And it's a blue laser pulsing every second or so. Let's call it a second just for fun. And what she's going to do is watch him fall in. Now, this is going to be kind of the end of their relationship, as we're going to see very soon, because this is going to be kind of the end for Jack. Well, let's see what happens as he falls into the black hole. So he falls in a bit more. From his point of view, he's just seeing the ship getting further away, and Jill sees him getting further away as well. And so he continues to flash the blue laser once a second, according to his watch. So he's got a timer. And on that timer flashes the thing once a second. That's what he's going to do for as long as he can. From Jill's point of view, she's seeing something strange. She sees it take longer and longer for the laser pulses in between each individual pulse. It's taking longer and longer for them to arrive. And every pulse that he sends as he's falling, each successive pulse has a longer wavelength. It becomes redder and it becomes fainter. It's losing energy, it's losing intensity, and the time interval between them is stretching, and it's going to longer wavelength and lower energy. Furthermore, as Jack further falls, he sees the outside world getting stranger and stranger. He sees the outside world become wildly distorted. Stars are changing position around him. He starts to see proper motion of the stars moving very, very, very fast. Jill, however, is seeing Jack's laser flashing maybe once an hour, slower and slower in between. And the laser flashes have now, as he gets closer and closer, maybe the laser flashes have been redshifted so very strongly that now she has to dial her frequency down to AM radio in order to actually to see the flashes. So now she no longer sees them. She's getting them in radio frequencies, and they're getting fainter and fainter. So if he started off with a really dim laser, she's not going to see it. Finally, he gets to the event horizon, and when Jack gets to the event horizon, she sees that the laser, there's one last pulse, and then another one maybe months or years later, maybe even never. And the next one never comes. So for her, she never sees the last pulse. And the very last one is extraordinarily faint. Maybe she had to dial up her receiver, put a gain on it, massive gain on it, build a huge antenna to try to receive the light. And it's extraordinarily long wavelengths, maybe tens of kilometers or hundreds of kilometers long. And she never sees another flash from Jack. But Jack doesn't know. He doesn't see this. Remember, for him, all laws of physics are the same. And that's what the equivalence principle says. So as he's falling, he's still ticking away one second at a time. Tick, 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 tick. That's what he's doing. And he's shooting a blue laser. So that's what he sees. The only problem is, as he crosses the event horizon, he feels some pretty strong tidal forces as his feet get ripped away from his ankles, get ripped away from his knees, get ripped away from his waist. Everything gets shredded and pulled apart, and eventually his eyeballs get pulled into pieces and bits. And it's just kind of bad for Jack. So it wasn't a very good fall for him. He might have fallen maybe an hour, maybe 15 minutes or something like that. But in the last few seconds, he had a big problem. And once he gets inside the singularity, well, whatever is left of him, whatever could possibly be left of him, immediately falls down to the center of the black hole, at the center of it, and gets crushed to infinite density in the singularity down in the center of the black hole, which is a very weird place down in the singularity, which is the point of no return. So let's see what some of these effects are that Jack and Jill experienced. One of the important effects is called gravitational redshift. And gravitational redshift is the redshift due to a photon climbing out of a strong gravitational field. So if you're at the roughly outside a black hole of about 1 solar mass, which is about 3 kilometers in diameter, then if you at about from 10 kilometers above it, maybe three times the Schwarzschild radius, and you beam out, say, a visible wavelength light, By about 100 kilometers, it's been redshifted down to infrared, and by 10,000 kilometers, when it finally gets out of the gravitational field, it's been redshifted to the radio. However, X-ray light that comes from extraordinarily hot stuff that's falling right into the black hole would be redshifted down to ultraviolet and then down to visible light by the time it gets to 10,000 kilometers away. So we would expect there to be extraordinarily redshift that would occur as it comes up. So that's what these equations on the right show. Z is the redshift, lambda observed is the wavelength that we observe it to be, and lambda emitted is the emission wavelength of the light. And Z, that's the definition of redshift, is the difference between the observed and the emitted wavelengths of light compared to the emitted wavelength. And the bottom relationship shows what the wavelength that we would get if we were standing off, say, an infinite distance away compared to the emitted wavelength. So that would be observed at such a far distance that we don't feel the gravitational pull of it all, say maybe 1,000 light years or something, and that's good enough. So then we would see that the R sub S is the Schwarzschild radius, and R sub E, capital R sub E, is the radius from which the light was emitted. And you can see that if the closer it is, the closer to radius emission is to the Schwarzschild radius, R sub S, that number gets closer and closer to zero. But the reciprocal of the square root of a number that's close to zero is infinite. So the wavelength gets longer and longer and longer and longer as you emit it from closer and closer and closer to the black hole. So that's gravitational redshift. The other thing that we learned is that we heard that Jack's clock looks like it got ticked slower because he thought it was a second. His watch always shows that it's going by 1 second at a time. However, Jill saw the intervals between the pulses get larger and larger and larger. And that's because of gravitational time dilation. So Jack's clock, as he's deep in the gravitational field, compared to what Jill's sees, they're different. And Jack doesn't ever appear to ever fall through the event horizon according to Jill, because his clock gets slower and slower and slower. So from Jill's perspective, if she could somehow see Jack and see the dim, dim, dim light that's extraordinarily redshifted from him, then she would see him stop moving and never get into the event horizon, because there would be one last image of his light coming from, say, the light that reflected off of him. Instead of a laser, maybe he just shone a light on himself. That would be deeply redshifted, and it would not show him moving at all. And therefore, from Jill's perspective, he never crosses the event horizon. He just moves slower and slower and slower. Because for him to cross the event horizon, from her perspective, would take an infinite amount of time, as we can measure from that equation that's across the bottom. And T sub far is Jill's clock on board the spacecraft, far from the black hole, and T sub deep is somebody whose clock is deep in the gravitational field. And what we see in this is that if you divide the T sub deep, whatever Jack is measuring, it might be 1 second. If you say, oh, he is how far from the center of it, we see that crazy square root, that 2gm mass of the black hole divided by the radius of the black hole, radius at which Jack is emitting the light, not now the radius of the Schwarzschild radius, but R stands for where Jack's emitting the light from, and then there's a c squared there. The closer that R gets to 2gm over c squared, which is the Schwarzschild radius, the larger and larger and larger the time becomes. And in fact, that's exactly the same thing that we saw with the wavelength. So the wavelength becomes longer and longer, and the intervals of time become longer and longer, according to Jill. So you get gravitational redshift and gravitational time dilation. And also notice that the redshift indicates that the photons are losing energy as they come out, and they take longer and longer and longer to get to Jill, which is interesting. They're traveling at the speed of light, and Jill might be only 100,000 kilometers above, or above the black hole. So why doesn't the light get to her, and say, since light travels, let's say she's 300,000 kilometers above the black hole, or 1 light second, why doesn't it take a second for the light to get there? Well, that's really weird because of time dilation. All right, so let's see what it looks like as Jack falls into the black hole. So if Jack's falling into the black hole, this is what he sees. So he's going to be spiraling around the black hole. See how this image shows it kind of spiraling. So as Jack falls into the black hole, we see him getting closer and closer and closer to the black hole. Eventually, he passes through the stable orbits where you can orbit stably. We get closer and closer inside of those stable orbits. He always sees the black hole beneath him, though, which is really interesting. Remember, the light can't get up from below. Eventually, he falls through the horizon, through the event horizon, and then all the way down to the singularity itself. And here he is at the bottom now. That's rather interesting. So what we saw with that is that the black hole was always below Jack, even as he got all the way down to the center. He fell through the horizon, he always saw stars above, and he always saw the black hole below. That's what Jack saw if he could somehow stay together against these massive, massive, massive tidal forces, which of course he can't. And we see there's massive redshifting of light as it's being redshifted around him, and all the light gets stranger and stranger and more distorted as he goes. And a lot of these images that you're going to see come from Dr. Andrew Hamilton, who is at University of Colorado, who is a major black hole researcher and has looked at the mathematics of it and published numerous things and made amazing simulations. So I provided a link here, and I'll indicate on those websites where his material is. But he's done some great TED Talks. He's been featured at the World Science Festival, and these are some fantastic things. And some of his ideas aren't properly given their due, so I'm giving them their due. Now, another thing that can happen, that does happen, as they fall into a black hole, as Jack falls in, we talked about he gets ripped apart. That's called spaghettification. So as Jack falls in, he gets both squished together and stretched apart. And that's the nature of that tidal interaction that pulls things together. So even before he gets inside the event horizon, he gets stretched and squeezed. By the time he would get to the event horizon, he would be narrower than an atomic nucleus, S size. He would be narrower than that. And by the time he fell through the horizon, the sizes of all his matter would be extraordinarily small indeed, possibly even as small as the Planck length. And we see way in the background, far, far, far away, not being affected by those tidal forces, is Jill in her spaceship maybe 300,000 kilometers away. And just to make sure that everything was normal, she also dropped a beach ball, and that beach ball got shredded, but had Jack seen the beach ball, he might not have jumped out of the spacecraft. Well, they had a bad time, apparently, going on that rocket trip, and she somehow convinced him to jump into the black hole, whatever that's about. Don't really know, but that's interesting. Anyway, so gravitational lensing is another effect that can occur, and we saw that, and that was the effect that we saw of all the light. The path of the light is being bent and redirected by the curvature, not the gravitational field, but by the curvature of space-time that is created by the concentration of mass as a black hole. So the observer is that kind of triangular IE thing on the left, and the black hole would be this reddish thing that's in the center, and we might have multiple images. And the light that comes from the object, which is actually the real object, the light would come from the top of the object, and it could be redirected to above and below. So you could actually see multiple images of an object above and below. The same object could be seen above and below a black hole because of the redirection of light by the curvature of spacetime. So curvature of spacetime can act as a lens and actually bend the curvature of the direction of light, and that's actually seen in, say, the deep gravitational fields of massive galaxy clusters such as this one. And this galaxy cluster has numerous arcs and curves in the background, and each of those is a gravitationally lensed galaxy far, far, far in the background. We can see this in a much more entertaining fashion. It's again by Dr. Andrew Hamilton, and what he did is he created a simulation where we pretended that the Earth is orbiting a black hole with a mass of 2,000 times the mass of the Sun. And we're going to pretend that this Earth somehow can orbit at 3 times the Schwarzschild radius. Now it looks closer than 3 times the Schwarzschild radius, but that's because the gravitational curvature has actually bent the light around so that we can barely see anything. But there's some features that we see as the Earth orbits, and it's not that the Earth is getting stretched and pulled. Remember, if you're on the surface of the Earth, the equivalence principle says everything's normal. It's just distant observers see something really weird, and we're distant. Everybody on the Earth, well, if they could survive the tidal forces, which of course they can't, but pretend they can, it's like super duper duper Earth and it's surviving it. There's a couple things that we see. The first is that as the Earth is on the right-hand side, it's going away from us. And so we have a redshift and a time dilation of going slower as it's orbiting. And when it's approaching us on the left-hand side, we see it's blue shifted, so it is a bluish tint as the light gets blue shifted as it moves towards us because of the rotation aspect. The Earth at this point would be orbiting approximately 80 times a second, so that's where that redshift and blue shift is coming from. And the distorted view of the Earth as it goes behind the black hole is the gravitational lensing due to the redirection of light that's reflected off of the Earth and comes to us from that source. So this shows multiple things: the gravitational redshift, the time dilation as it orbits, as well as the distortion due to of light's path as it orbits a massive black hole such as this. So that's what we call an Einstein ring, and the Einstein ring is a perfect example of perfectly aligned something in the background. We see that white image in the background. Maybe there's a bright star or an extended object, and it's perfectly positioned so that the light gets redirected in a ring, and that's what we call an Einstein ring. Now, if we orbit a black hole, we can then say, let's get really close and orbit a black hole, and there's an unstable circular orbit, not a stable circular orbit, but an unstable circular orbit at 2 times the Schwarzschild radius above the surface. So 3 times the distance from the singularity at 3, then that's the last stable orbit. And what we find is that if you're at this location, if there's a supermassive black hole like we find at the center of Milky Way, it would take about 10 minutes to orbit at this height. But in this unstable orbit, if you turn on your jets just a little bit, you can either go up or down, and any motion at all would send you either careening into the black hole or spiraling quickly outward, any tiny thrust. And there's also a weird element. Those kind of 2 poles are really, we actually are seeing the north and south pole of the black hole in our view. And if we got even closer, we would actually see the entire surface of the black hole, the entire event horizon, all at once. And that's when we are actually passing through the event horizon, is when we see the entire thing at once. Now, if you orbit the black hole at the speed of light, and you're right at nobody can travel at the speed of light, but if you're orbiting at the photon sphere, which is 1.5 Schwarzschild radii, then this is what you'd see. So this is the view of a photon as it travels at 1.5 times this 1.5 Schwarzschild radius over a black hole. Again, this is from Andrew Hamilton's website. And if you just fall in, this is what Jack saw as he fell straight in. As he looked up and fell straight in, the universe above him actually shrank. Notice it got dark around it. So he had a full sky view, and that full sky view shrank and shrank and shrank, got bluer and bluer and bluer, brighter and brighter and brighter, and more and more intense, until all of the light of the universe were coming down to him from a single point of infinite intensity. And that infinite intensity is as he is falling through the event horizon. So that's what you would see if you just looked straight up and fell straight in. There would be infinite blackness around from where light could not reach you, and it would get darker and darker and darker, and your view would get smaller and smaller and smaller with all light coming from one point. So what's inside a black hole? No one knows. No one knows at all. There's nothing to know. It can't be known because there's no way to understand what goes on. However, we can make metrics, and we can make space-time metrics or measurements of space and time inside of there. That would, but likely what happens at this point, the understanding is that the mass collapses until it has 0 radius and the density becomes infinite, which is kind of weird, but it's inside of an event horizon, so we'll never know really what happens. We have no idea what happens. Might be something that stops it. Maybe it actually doesn't reach the singularity. Maybe nothing ever does, because everything below it is still falling at faster than the speed of light towards it. Now, this is all pretty crazy and everything, but let's think of a new way of talking about it, which is what Dr. Andrew Hamilton likes to propose. He created a model of black holes, which is very interesting and helpful to understand, so you can really get a conceptual understanding of black holes. He called it the river model. So we can think instead of having curvature of spacetime, a totally mathematically equivalent way of thinking is to think of a flat spacetime where space is rushing, where space itself is moving towards the singularity, and everything is trying to rush against that. So we can think of photons as our fishes, and the fishes are rushing against it. But if the waterfall of space is going at the speed of light, well, then the fish that's a photon can't go up that thing anymore, and it gets stuck and it gets carried down. And inside the event horizon, then it's too fast. So here's what we mean is that the event horizon, those arrows show the rate at which space is flowing towards the singularity, and it's falling in free fall towards the singularity. Space itself in flat space-time. We can pretend now that space is not curved. Rather than say it's curved, we say it's flat, but that's flowing. So if we then think of a flowing flat space, and each of those arrows represents the escape speed, or the other way is the free fall speed. So that is the speed at which space is flowing, and once it reaches the horizon, it's flowing at the speed of light. So inside the horizon, the space itself is flowing towards the singularity faster than the speed of light, so therefore nothing can go faster than the speed of light. Space can go faster than the speed of light, but no thing can, and space is not a thing, so therefore it can go faster than the speed of light. I'll let you ponder that little bit for a while. And the idea is that nothing, since nothing can go no thing, no light can go faster than the speed of light, therefore the space-time flow overwhelms the flow of things and carries it down like a river. And so that's a mathematically equivalent way to the Schwarzschild metric. And that's a very easy way to think about it. And it's exactly equivalent to what I'm about to show you, which is the Schwarzschild metric. This is the way we measure space and time inside and near some sort of black hole or a spherical object. What this equation means is that we have, let's just look at the pieces. The little thing on the left-hand side, ds squared, means that's the actual physical length squared. So it's derived from the concept of the length of a triangle in Pythagorean theorem, where the hypotenuse squared equals the sum of the two sides squared. But now we take it in terms of a curved space-time. We're going back to curved space-time, away from the waterfall concept, back to Karl Schwarzschild metric from the 1930s, and we see 1917, and we see that there is a term that describes time, which is dt squared, which is a square of a tiny interval of time times the speed of light squared, and then you multiply it by that funny factor in front. And then we have dr squared, which is a tiny interval of radial distance from the event horizon up, and that's divided by that funny thing. And then we have the d omega squared, which shows that we're going to move left and right a little bit, maybe not up and down, but left and right and back and forth with respect to the surface, the event horizon itself, at some distance. So this is our way of measuring the shortest distance between two events in space-time. And as we use this thing, the actual distance is the ds squared. That's the physical distance. But each of the dt, dr, and d omegas are coordinate distances. They're not distances, they're the coordinates that are measured locally by, say, Jack as he falls in, or Jill as she's far away. But when we want to say, well, how far is Jack from Jill, then we are measuring ds squared, and we have to sum up all the little tiny bits to see how far he actually is. Well, let's actually make it a little easier for ourselves and pretend for a while that gravity is weak. So we go back to our energy equation, mp squared equals gm over r squared, and let's assume that we then say that v is now the speed of light. So if the gravitational potential energy is much, 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 much less than the rest energy, or the E equals mc squared thing, then gravity is weak. And we can transform the other equation in the previous equation into the one we see here, and that we can play with this thing and say, what does it take in order to make a satellite orbit the Earth at a fixed radius above the equator? And we can actually use this equation to derive the classic standard equation of the speed of a circle is equal to gm over r. You can use the equation above by saying that it's at a fixed distance, and it's going at a fixed circular speed. We're just going to assume that, and use this equation, this metric, this way of measuring space-time. And then once we get a relationship, we can say, now pretend you kick it a little bit above or outside that orbit just a little bit. And we find that that is the shortest possible distance in space-time, is to make a circle. And that circle then is what we call a world line. And then we can derive rather rapidly from this concept of just kicking it a little bit and saying, a little bit longer, a little bit shorter. Can we actually make it shorter or longer? And the answer is you can't. And once you do that, then you derive from those concepts and using this metric the speed of something orbiting in a circle above a planet of mass m of at height r. And that's what that means. And that's good to know because general relativity has the solution of the Schwarzschild metric, which then we can use to derive Newton's laws. So all of Newton's laws of gravity are actually inside that middle equation. They're just hidden in there, and you just have to solve it using conditions and concepts, and you can derive everything else. So all of Newton's laws of gravity and motion are put inside this measurement of space-time that we see in the middle. Now there is something really funny I should want to highlight to you, is that gm over cr squared, which is really kind of funny, because if we look closely, inside the parentheses, you've got 1 minus that quantity. And so what is the 4 things? You got the 4 things are a 2, it's just a number, and g is Newton's gravitational constant. M is the mass that's doing the thing, that's gravitating. C squared is the speed of light squared, and r is the distance away from the event horizon of a mass of m, which is interesting. Away from the surface from it. And that's fascinating because g is a number and c squared is a number, but mass is a measurement and r is a radial distance. So somehow we're converting mass into length. Let's see what that really means. If we then say, well, mass has to be converted into length, so g over c squared is actually a conversion factor. And that's how we convert. Actually, I forgot the number 2 in there, so let's just throw in what's the number 2? Yeah, let's put a 2 on top. So 2g over c squared shows how you convert gravitational energy of mass into a length. So we just simply divide the one by the other, and we find that the conversion factor between meters and kilograms is that there are 7.416 times 10 to the minus 28th meters in a kilogram. That's a weird thought. Well, if you have a lot of kilograms, then that length becomes large. And then we say, well, let's say we have 10 to the 30th kilograms. Oh wait, that becomes about 1,000 kilometers, 1,000 meters, which is the Schwarzschild radius of the sun. So we can actually derive from this concept that mass is actually a length. Funny thing to think about. So we can then think of mass as being a length, so another interpretation of that is space is actually longer near massive objects. And since space is longer near massive objects, it wouldn't be like dimpling into some other place, it's just simply bigger. And the way we can think of it as being bigger is that those grid marks are coordinate marks. Think of it as a topological map that you might use going up and down a mountain when you go hiking. And so those grid marks display, if the grid marks are close together, then you know that you're going up and down a very steep hill. But if the grid marks are far apart, which is kind of what we see in this image, it's kind of like it's been stretched, then if they're far apart, then there's no hills there. Or if they're regular, way out at the edge, they're regular, and there's no hills or bumpiness. But what we could have done with this thing is just put all the grid lines really close together. They would be squish together inside of this image. Instead of making a dimple, just have them compressed together into a point. And if they're really close together, then space has been stretched, and therefore it's been made longer in those areas. And another way to think about it then is that we can again bring back our concept of the way space is flowing, we can think of space as flowing and it's carrying the mass along with it. And mass is the thing that also makes the direction from which it flows. So mass affects the flow of space-time in the river model, but it also in the curvature model, which are this exact same way of thinking, just slightly different words, is that the mass tells space-time how to move, and space-time tells mass how to move, and mass tells space-time how to curve. So the dimple of space-time is created by mass, and then the mass then says, oh, I made a dimple, I got to follow the dimple. And so as it moves, it must orbit in a dimpled sort of shape. And that's a classic concept that was coined by Wheeler in his textbook. And so that's the way we can best think about space-time curvature and its interrelationship. Well, how can we see black holes? Well, what can we see about black holes? If they're black, how do we hope to see them? And we look for their gravity on their surroundings because we're looking for maybe a star orbiting something that, well, isn't there. Or maybe there's a huge amount of X-rays that are being emitted by gas as it falls into a black hole. And that's what we call X-ray binaries. An X-ray binary is a bright source of X-rays that can be seen by something like the Uhuru satellite or Chandra X-ray Observatory or the Fermi space satellite or even the New Star Observatory. And let's say you have a spectroscopic binary, which is a star that has emission lines and it's moving back and forth rapidly, and the other one's invisible. And maybe you find that the mass that it's orbiting is very large. Or and therefore it might be really close if they're spectroscopic, and the visible star dumps mass on the companion, and as it dumps mass on the companion, the gas gets hotter and hotter and hotter until it emits X-rays, and that makes an X-ray binary. And you can by looking at the orbital parameters as well as the flickering of the X-rays, can give you the parameters and size of the black hole. And so if you find a black hole candidate, you're looking for something where the mass is about 3 times the mass of the sun. So what are some candidates? They have to be bigger than 3 times the mass of the sun, and that means it would be too big for a neutron star. And there are about 20 or 50 or so, more than that. There's about 50 or 100 confirmed black holes candidates, and I'll post those. There's a definite little list of black holes in like a Wikipedia that continually grows. So I have an out-of-date slide here. So here we go. But the first one to be discovered was Cygnus X1. We're going to take a look at that as a mass of 14.8 solar masses, but most black holes are between 4 and 10 solar masses, except for the really big ones, which are billion solar mass black holes or million solar mass black holes. Actually, our galaxy, well, there's 1 billion or so stellar-sized black holes in our galaxy, because there's a lot of iron in our blood, and that came from the supermassive explosions of stars as they've exploded. So we got to figure out where they're at. And then what are the observational evidence? Well, we're going to focus on Cygnus X1. It is the brightest, one of the brightest X-ray sources in the sky, and it's in the constellation Cygnus, and it's probably the first thing that was accepted to be a black hole. It was discovered in 1964, and we know now with measurements that its mass is about 14.8 solar masses, and its distance is over 6,000 light years. Now, the reason that we think it's too small is because it was because of how fast the X-ray bursts come. So if you have a millisecond X-ray burst, that means it can't be larger than 1 light millisecond, which is 300 kilometers. So the largest event, the event horizon, must be smaller than 300 kilometers. Therefore, we think that something really small, that event horizon of 300 kilometers, is the outer limit for the event horizon. So that's where the X-ray bursts are coming from. So they have to be falling in before then, but there isn't anything past those X-ray bursts. So they kind of fall in and they're done. It's not like there's a massive burst that occurs and there's just these little tiny bursts that go pop, 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 pop. And it's not like there's something that glows in X-rays as though it's glowing from the surface of something like a neutron star with its massive X-ray binary output. For a black hole to be 14 solar masses, the star that made it had to be about 40 solar masses. And there's no supernova remnant around there. So we think that a 40 solar mass star would have simply collapsed directly to a black hole at the end of its life. which is a wild thought for its exiting strategy. Finally, we know that X Cygnus X1 is in a high-mass X-ray binary system, and we know that their separation is about 1/4 of an astronomical unit, which is closer than Mercury orbits the Sun. So we got something 14 solar masses, and another object that's somewhere between 20 and 40 solar masses, and they're orbiting at a distance that's smaller than the orbit of Mercury. So you're going to get a stellar wind as the big O and B type blue supergiant, which has been observed, dumps material onto a companion accretion disk around the X-ray source. And as it gets closer and closer and closer, it gets hotter and hotter and hotter, and the inner accretion disk gets to be millions of degrees, and as some of that material goes out into jets, but those jets aren't observed with respect to this, but it's posited they exist, and a significant fraction of it, that's where we see the X-ray burst, is material just falling into the center of it. And there's a periodicity of about 5 or so days, as they zip around as they orbit in about 5 days. Now the whole system itself, this pair, seems to belong to a stellar association of O and B type stars called Cygnus OB3. And if it's part of that organization, then the whole thing is about 5 million years old, which is where we get the concept of the masses of both of that star, and why we think it has to have that mass. Because if the whole association is 5 million years old, then it had to have evolved fast, and it had to be about 40 solar masses in order to evolve that quickly. So let's take a look at where it is in the sky. This is the location of Cygnus X1 in the sky. This is the location of Cygnus X1 in the sky, and you can actually see the star in there. And if it's zoomed in, we can, in theory, zoom in. There's an image by the Chandra X-ray Observatory, and the X-ray observations. This is the X-ray image of Cygnus X1 taken by the Chandra X-ray Observatory as they orbit each other every 6 days or so. And we see that it's actually kind of big. It's about 1.5 arc minutes. Remember, the moon is about 30 arc minutes across. So this image is about 1/10 of, half of a tenth is about 5% the diameter of the moon. So it's like the same size as a relatively large crater that can be seen with telescopes on the surface of the moon, or small telescope or binoculars on the surface of the moon. So that's how big this image is. It's about the size of a large crater seen through binoculars on the moon. So if you had X-ray eyes, you could see it, and you'd actually be able to make out its size. Furthermore, we know how we to find its size is by looking at the X-ray spectrum. So the Chandra X-ray Observatory is able to actually get the spectrum of light, and we find that it has a bright emission feature that would be due to iron falling into the center of it. Now, if it gets hot enough to emit X-rays, then it's dense enough, the gravitational potential energy is dense enough for it to actually become, to do some nuclear fusion close by. Actually, it's mostly heat and friction that would do the trick, but there would be iron nuclei, and those would emit enormous amounts of X-rays. And the width of that emission line, that bump up, not the spike in the middle, that's where the main emission's at, but there's a width to this line, a very large width, and that's because it's being gravitationally redshifted and blue shifted as it goes around, and it's broadened because of gravitational redshifting and the Doppler effect of zipping around in a disk. So here's what we think that the Cygnus X1 probably looks like, with that bright O and B type supergiant next to it, dumping material as it gets just to the balance point where the pull of the 14 solar mass black hole is greater than the pull of the 40 solar mass blue giant, and it falls from the blue giant into the disk. There's a hot spot where it contacts the disk, and the material rotates and rotates around until it finally falls into the black hole. And you actually can't see the black hole. We see a black area, and that is not where the black hole is. Remember, a black hole of 40 solar masses, that's only going to be about 30 kilometers. And remember, a typical star like this is going to be a star like the blue supergiant over there. That's going to be bigger than the sun. So remember, go back to our scale size thing we did at the beginning, and you actually can't see the black hole there. Even that dark spot would be invisible. So the X-rays are being emitted even tighter there, so this artist concept is still flawed. We'd have to get very, very, very close in order to actually see the event horizon, or even get close enough to see it. And there would be jets that would be coming off of it, And because of this formation of material falling into a black hole, Cygnus X1 is called a microquasar, and we'll see what that means when we talk about galaxies in the future. Funny enough is we can go also and discover other things about black holes. The movie Interstellar had the most accurate depiction of the appearance of a black hole, and they did a massive supercomputer imaging of what a black hole would look like. And so there's a spaceship kind of floating around next to a black hole, Gargantua, a very supermassive black hole with a disk around it, and that disk is around it, but we see it apparently above and below because of the gravitational lensing of the material around it as the spaceship goes around. The movie Interstellar was designed to actually try to show a black hole in its most accurate depiction that was ever done in any Hollywood feature. So this is a relatively accurate portrayal. There were some Hollywoodish features, like we didn't get rid of, there would be certain squarish features to it, as well as lots of redshift and blue shift, so you'd only see one side of it at a time. But it's Hollywood, so they had to do some stuff. Anyway, so look up Kip Thorne and Interstellar to see more about that. Also, we can learn about different kinds of black holes. There's one at the center of our Milky Way, and this is from the European Southern Observatory looking directly at it. And there's a supermassive black hole at the center of our Milky Way that's about 4 million times the mass of our sun. And we know it's there because of the effect of stars that are around it. And Andrea Getz's group at UCLA has been studying this for over a decade, over 20 years, looking at individual stars moving in their orbits around the central supermassive black hole in the center of the Milky Way, and is deduced by the motions of stars over the course of 20 years that are moving incredibly fast that there is something really big there, about 4 million times the mass of the sun, and it would be about the size of it would be comparable to the size, something about the size of the inner solar system. But that's 4 million solar masses of black hole. Next, we go to the outer skirts of the cosmos, and remember there's a jet coming out, so where there's huge massive jets emitting X-rays from distant galaxies, we can expect that there's a supermassive black hole in this galaxy, M87, and M87 as its jet appears in radio frequencies, and it emits this crazy jet, and that is also the result of a supermassive black hole, material falling into that black hole and spiraling around magnetic fields and being ejected out into intergalactic space. But black holes aren't really black. General relativity says they're totally black, but that doesn't take into account quantum mechanics. And quantum mechanics says some really interesting things. Quantum mechanics, according to, if you pull that in, Stephen Hawking posed that in the severe gravitational field around a black hole, the amount of gravitational energy of the gravitational field is so great that it can actually create subatomic particles and light. And as it creates them, one particle could fall into the black hole and its antiparticle could leave the black hole. And if that happens, it's emitting particles. And that can be considered thermal radiation because that would be at a particular temperature according to the size of the black hole. So the smaller the mass, the hotter it would be, and that's what's called Hawking radiation, and therefore it would be a faster evaporation. But if for black holes that are big, like normal things, it would be very, very, very tiny because a solar mass black hole would take 10 to the 64th years to evaporate. Well, the universe is only about 10 to the 10th years old, so that's about 10 to the 54th times the present age universe. And Hawking radiation is a very interesting concept. It's most likely incredibly unimportant for today, but it will be an important process for the production of light and energy at the distant future of the universe. So what kind of black holes are there out there in the cosmos? Well, once we get to things that are sized white dwarfs and neutron stars, there are stellar-sized black holes, there are supermassive black holes, but intermediate mass black holes between, say, 100 times the mass of the sun and less than 1 million times the mass of the sun, they're rare. Stellar mass black holes seem to be extraordinarily common, and they're easy to make by making supernovae explosions of 40 solar mass black holes. Well, it's not easy to make, but at least that's commoner than intermediate mass black holes. And supermassive black holes are in the center of pretty much every galaxy, and there are at least 1 million solar masses. But determining the intermediate mass solar mass black holes, that's a puzzle that's currently out there among all of astronomy, and nobody really knows what's going on with that. So that's a lot about black holes, and they're really fascinating objects, and we'll be talking more about them next time. See you soon. Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This time we're talking about the results of the most massive stellar explosions that create black holes. They're the supermassive stars that are much larger than, say, 15 or 20 times the mass of the sun. They do weird things. They'll either explode as a type 1 supernova and form a black hole, or just collapse down to a black hole as a collapsar. But we're going to talk about how we know this and the history of it by looking at gamma ray bursts, which are the last vestiges of the formation of a black hole. So let's get going. The first thing is that why do we think about gamma ray bursts at all? Remember, gamma rays are the highest energy form of light, the shortest possible wavelength. They have the highest energies. They're incredibly short wavelengths that we talked about in the spectroscopy and nature of light discussions a while back. But what happened back in the 1960s, during the Cold War, the United States and the Soviet Union realized that all these nuclear bombs they were testing all across the Pacific and in Siberia were causing a huge amount of damage, and it looked like things were going to get out of control. So what people did is they said that the people said, well, we better do something about that. And the president of the time said, let's sign the nuclear test ban treaty with the Soviet Union in 1963. When that was done, it was also trust but verify with the Soviet Union, and researchers at the Los Alamos National Labs built a series of satellites called the Vela satellites. And their goal was to orbit in space and beam down to Earth this constellation of orbits. And their goal was to look for gamma rays, because gamma rays happen when nuclear bombs goes off. So either look for gamma ray detonations in space, which would be part of the nuclear test ban, is a confirmation that nobody's doing any nuclear bombs in space, or on the ground, because they would also form new gamma ray bursts on the ground. So a constellation of Vela satellites was launched. Not long after their launch, on July 2nd, 1967, two of the satellites saw a gamma ray burst, a flash of it that didn't look like a weapon signature. The weapon signature would have radioactive decay of elements, so it would last like a few seconds. It would be very localized to the surface of the Earth, incredibly bright, and would cause a bunch of different things. But so what they did is they said, well, this is kind of weird, but they ignored it for a while because it didn't look like a nuclear bomb. Then they started seeing more of them, and they found that the Vela satellites, they were wearing out, so they launched some replacements, and some additional satellites, and they were able to clearly demonstrate by using occultation with the Earth that they were not coming from the Earth, they were coming from space. And so since they discovered they were coming from space, they declassified their information and published it in 1973, and thus began gamma ray astronomy. And gamma ray astronomy kind of languished until the launch of the Cosmic Gamma Ray Observatory, the Compton Gamma Ray Observatory, with its onboard instrument BATSE. So this was an incredibly tantalizing mystery, and not knowing where these gamma rays came from, which were the highest energy form of light. No one had ever thought they would happen, but they were coming in these flashes. It's not like there was a constant gamma ray source like the sun or something. Nope, the gamma ray flashes were not coming from the sun, they were not coming from the Earth or the moon, or what seemed like any of the planets. They were coming from the stars. And so somebody figured, well, what caused them? Nobody literally knew, and it was an incredibly hot topic of research. So in 1991, NASA launched the Compton Gamma Ray Observatory as one of the great observatories of NASA's great fleet. which include the Hubble Space Telescope, Spitzer Space Telescope, Chandra X-ray Observatory, and the CGRO. Now, it's one of the more important things for gamma-ray bursts was it carried the burst and transient source experiment, the BATSI, burst and. So some people say BATSI, but I say BATSI because A is spelled like and. Anyway, but the good thing is it had all these little detectors, one on each corner of the observatory, which you see here being launched from the Atlanta shuttle in 1991, and between 1991 and 2000, it observed over 2,700 gamma-ray bursts with its instruments. They found that the gamma-ray bursts lasted from about a quarter of a second to up to 30 seconds, and they came in the form of thousands, if not hundreds of thousands, of individual gamma-ray photons from specific places in the sky. And there's something interesting about this, to me, was that I graduated high school in 1996, and in college in Mankato State University, my undergraduate advisor, John Hakala, made his entire career out of looking at the BATSI data. And so in my junior year and my senior year, we worked on some software that would actually determine where these things are coming from in the sky. So it was really interesting to be a college student and then working on this. And then I actually went down to the American Astronomical Society and gave a presentation about the nature of the software on a slightly different way. But what Dr. Hakala did later is that he moved on to Huntsville, Alabama to work on that and discovered eventually that the BATSI gamma-ray bursts were isotropic, meaning they came from all locations in the sky. So the colors here indicate the amount of total energy, and the redder they are, the greater the total energy, the greener they are. The middle in blue is the least amount of energy total. You can see that all of these things are evenly distributed across the entire sky. And this is a galactic coordinate where the center of the Milky Way is in the center. Galactic north is at the top, galactic south is the bottom, and go round and around as we see that. And the dots represent each dot is an individual source location for a gamma-ray burst as seen by the BATSI instrument. So if you compare that to an optical image of the Milky Way, we see the Milky Way is confined to a disk with some stars above and below, but the gamma-ray bursts clearly are not in the plane of the Milky Way predominantly. They don't even seem to match. They seem like they can go almost straight through the Milky Way center, although there does seem to be a bit of a zone of avoidance smack in the middle, which kind of makes sense given that the center of the Milky Way is directly in the center. So that kind of makes sense. In any event, what we see is that it's not confined to the plane of the Milky Way, and that was a major discovery that became elucidated a couple of years into the BATSI into it, and it didn't take until 2000 for this to be determined. But this was known well into as it progressed. So then the thing was, what the heck are they? What the heck was doing it? Because the BATSI probe could actually give a burst, a transit profile. It could give a rough spectrum of it. It knew when they started, when they finished, and how bright they got through time, and they could actually get the rough spectrum of them from different instruments. And so what we find here is that nobody really knew what the heck they were, and this was an open-ended question for a long time. And what were they? White dwarfs, pulsars, new supernova, something in a globular cluster. Maybe quasars were doing it, or Seyfert galaxies, or BL-lac objects. We don't even know. Nobody knew. So everybody was saying, we can't tell. But we have to find an optical counterpart to these gamma-ray bursts. Somebody's got to find them and see them in order to see what the heck they are. So they said, well, we have to be able to see the gamma-ray bursts because they only last a fraction of a second or a few seconds. So we need something that's going to get over to them quickly in the sky so that when they happen, we can see this fading glow of light, because we want to see the gamma-ray burst and then see the light from maybe visible. And they needed new satellites and new communication. But the internet really was in its infancy back then, so it was hard to do. So people had phone messages and things like that, and they were contacting that way. Then in 1996, the Bepo-Sachs X-ray satellite, this was during the operation time of CGRO, was launched by the Italian and Dutch, the Italian Space Agency, and it was an Italian-Dutch satellite launched in 1960. It lasted about 7 years, and it was able to detect the gamma rays and then swing to a different swing to look at them with a lower energy X-ray telescope. So in February of 1997, 1 year after I finished graduate school, not in New Mexico, but in Texas, it caught the first afterglow of gamma ray bursts in X-rays, and then it was followed up with a large ground-based telescope, the Herschel Observatory in the Canary Islands, and it was actually infrared glow from it was seen 20 hours later, and there was a little tiny faint galaxy at that position. Now the hard part was that nobody could get a distance to this thing because the little faint galaxy was really faint, and so nobody could get a distance to it by getting a spectrum. But didn't have to wait long. A few months later, 1997 in May, just 3 months later, another burst occurred, and the follow-up by a ground-based observatory was done in 4 hours, and the host galaxy was found to have a redshift of 0.835. That meant that the galaxy was over 6 billion light years away, and this was the big breakthrough. Those are the two major breakthroughs that said, these things are cosmically distant. So in 1998, another burst was confirmed in the same place as a supernova. So a star was seen exploding. And then it's like, wow, now it's not some white dwarf or something. There was a supernova that went off. We know where it is. We know how far it is. And then and other satellites such as the HETI 2 were also launched. And HETI 2 satellite was the dominant contributor of looking for gamma ray bursts between 2000 and 2006. However, at the end of that season, the Swift gamma ray satellite was launched in 2004. It was renamed the Niels Gehrels Swift satellite earlier this year in 2018, after the person who was the principal investigator who recently passed away. But it was launched in 2004, and that observatory, which is still going, contains 3 telescopes. It looks at gamma rays, it has a gamma ray burst detector. It can swing around and look with X-rays in low resolution, and then it can look in higher resolution with optical light. The best part about it, though, is it allows it to detect a whole bunch of things rather rapidly. When a gamma ray burst is detected, the telescope is a spacecraft, so it slews as fast as it can in a few seconds over and points the X-ray telescope and the UV telescope at that location, pinpointing the location of the source. So it gets a rough general location in the sky, and both these X-ray and UV telescopes are wide field. So the telescope coordinates are then immediately emailed and then circulated now by email, because internet, hello, and it sends it around within about 5 minutes of the telescope doing its slew, and that allows ground-based observatories to follow up. I remember this, and so what's been happening with this particular thing is that as of 2015, the Swift Observatory has seen over 1,000 gamma ray bursts and has communicated to them all the way down to the ground, and its 1,000th observing thing was in 2015. And you can see it also has seen an isotropic distribution, and overlaid on that isotropic distribution of dots is the Milky Way in infrared. So we can see that they're not confined to the plane of the Milky Way, and they're not necessarily associated with the center of the Milky Way. They're cosmically distant. And so gamma ray bursts, we now know, come from, as we saw, came from, at least many of them seem to be coming from distant host galaxies. Then, in 2008, 4 years after Swift, the Fermi Gamma Ray Telescope was launched, and it has what was a thing called a Large Area Telescope, or LAT, and it can detect very high energy gamma rays and able to make make full, very high resolution maps of the sky in gamma rays. And this is fascinating because when it was launched, it created a whole bunch of new mysteries. And there was where does the gamma ray sky have now as a steady background? And it actually found what that was. It's like, wow, what is the background of all of the gamma rays that appear to be in the sky at this high energy level? And the largest known gamma ray burst to date, well, at least in 2008, was known to have, and the gamma ray burst had an energy equivalent of about 9,000 ordinary supernova was seen. And in 2010, the Fermi Gamma Ray Telescope actually showed that most gamma ray cosmic events were probably triggered by supernova remnants or collapsing black holes. In 2013, it detected the highest known photon ever recorded, which is 94 giga-electron-volts. That's a pretty high energy gamma ray. If you wish to know how much that is and say, well, it's not very much in terms of watts or joules, but it's the highest known individual photon that's ever been recorded. So it kind of doesn't look like a real telescope. It kind of looks like a box. See that gray box in there? That gray box is the detector. And each of those detectors has these funny subsets of boxes, and inside of each of them is a way of actually detecting the light. And here's how it works. The gamma ray, which is that kind of diamondy thing with a gamma inside, it comes from the top, and it goes into the telescope box. And what it does is there's a whole bunch of foil, and these foils have voltage differences across them. And what it does is that the gamma ray hits this foil. Each of the gray lines is a piece of foil, like a gold foil. It's not, I forget exactly the material of the foil, but when it hits the foil, it can interact, the gamma ray can interact with the particles in the foil. And when it does so, instead of being a gamma ray, it can interact with the material in the foil and create an electron-anti-electron pair. And that's what's happening when the two arrows diverge. That gamma ray has enough energy to create an electron-anti-electron pair, and then that tracks through the detectors, which are the dots. And the detectors say, well, how fast did it go through, and what direction did it go through? And by doing that, you can trace back where the gamma ray came from. And the calorimeter, which is where the electron and the anti-electron go, that deposits the energy of the electron and anti-electron and tells you exactly how much energy the photon had. And so that is how they measured the direction and the energy of a given photon. And so they can detect them all the time. And so the one of them that was detected, they kind of look like this in the sky. And so when they're found, they just look like bright points, and eventually they make a little dot, a little extra set of spots in the sky, and that's what they look like. And this was an extreme gamma ray burst from 2009. But let's take a look again at that one from 2013. And in 2013, in April 27, so gamma ray bursts are named. Every single gamma ray burst has a name. And they're named by 2013, 04, April 27 is the 27th day of April 2013. And A means that's the first one discovered on that day, because they're sensitive to find more than one per day, and that's happened. And in this time, it found the most energetic gamma ray burst ever detected. And we can see that this is the gamma ray sky image, a full sky image with LAT, that it was taken on that day. And there's a higher resolution version of that that's overlaid to show you just how much energy was on it. I think they rested the LAT on it for almost 2 to 3 hours. It was still emitting gamma rays for hours. And so we can see that this thing is extremely bright, extremely luminous compared to the background radiation. There are background gamma rays that occur. That's what all those blue dots are. Those aren't gamma ray bursts. That's just background gamma ray light from somewhere, from out in the cosmos. But they're not qualified as gamma ray bursts. It's just background gamma ray light. So this is a burst, and we'll see what that really means in a bit. But let's just take a look again at Fermi's sky map. And this is an all-sky map that's taken by the Fermi Space Telescope. And we can see that, yes, there is a significant amount of gamma ray emission that occurs in the Milky Way. But the blue shows there's all these spots of gamma ray emission, this background radiation. We also see a blazar, which is something that we're going to talk about later, and it's looking down the jet of a supermassive black hole that is billions of light years away. We also see 3 prominent pulsars in the Milky Way: the Vela pulsar, the Crab Nebula, and the Geminga pulsar. And the Vela was a supernova remnant that exploded about 11,000 years ago. And the Milky Way center also emits gamma rays as well. So the Fermi Space Telescope has seen numerous things, and most of those faint blue dots that we see in the background are due to light gamma rays that are emitted by material falling into supermassive black holes. So that's where most of the sources come from. So let's see what a gamma ray burst looks like. Here's an example from the Swift Space Telescope. We can see the little graph on the left that shows how bright it gets with time. And what we have is a picture from the ground of a particular location in the sky, and from the ground of the gamma ray burst, and then the UVOT, which is the ultraviolet telescope on board the Gerald Swift Observatory, and there's a tiny, tiny, tiny ultraviolet dot that is there in ultraviolet, but the ground you can barely see it, and the ultraviolet you can see it too. But the gamma ray burst that we see there's a background sort of gamma ray glow, and all of a sudden you get hundreds of thousands or hundreds of gamma rays per second. And so what we're seeing here is that there are over 200 gamma rays emitted inside of fractions of a second. So these things can receive thousands or hundreds of thousands of gamma rays, but at an individual interval of time, you see that we're literally counting individual photons that come into the Swift Space Telescope. And it rises as a burst and fades and then lowers again, then maybe there's a little bit of an after bump later. But that's what a burst profile looks like. Now, all these burst profiles are slightly different. So there's something really energetic extremely energetic that's creating these gamma ray bursts, and we can see that this is an energy range of moderate X-rays, or moderate and weak gamma rays from this particular sensitive region in the gamma ray burst of the Swift Space Telescope. That's what that 15 to 350 kiloelectron volts means in the upper right of the profile. And notice the length of the burst starts at 0 and goes no longer than a second, and most of the burst is done by half a second. So it kind of starts at a quarter of a second. So you see that there's like a background, and then foreground, and then it triggers the alert, and then it records the alert. And the trigger happens at about 0.2 seconds in. And when that trigger occurs, it sees that, it rises to a peak at 0.4 seconds after time, and then is done by 0.06 seconds. And maybe some after bumping for about a second. But the vast majority of it is done in less than a half a second. So how do you find these things? That's what the Swift telescope does. It slews quickly over to look at the ultraviolet, UV, and then X-rays as well. All right. This is typical of the profile, because when we look at the BATSI instruments that my advisor John Hackala looks at, here are 3 from the early launch platform of the BATSI Observatory, and I give you the where you can actually download these too, and we'll go look at those in just a second. And we can see some of them are quite energetic, and none of the profiles look identical. Sometimes they're long, like the middle one is many tens of seconds long, or they can be incredibly short, a fraction of a second, like on the right-hand side. Or they can begin and go to a really fast peak and then drain away, just like we see in the first one. Look, there is almost no periodicity to these things. However, there is some bumpiness, and that is a subject of active research, is finding patterns inside of these things. And that's what my advisor, John Hackala, has just found, has a recent paper that discusses that, and we'll talk about that. So the hunt has been on since the 90s to discover patterns in the behavior of these gamma ray bursts. All right, so here's more of the gamma ray burst from John Hackala's. Well, he wasn't one of the BATSI members, but he's been active in doing data research on the extensive data set of BATSI. And what we see is that look at all these different kinds of data sets, and each of the y-axes on these things is thousands of photons counted per second. So these are incredibly energetic things. And it's like, what is the real profile? So it's just very puzzling exactly what's making these things. And if you then group, well, how long do they last? If you take the entire BATSI catalog and say, how long do they last? You find that there's 2 groups. There's a short period group with that peak in the short periods, it's at less than a second. And then there's long period ones that are between, let's say, 10 seconds and up to a minute or so. So there's 2 basic peaks. That means there's 2 basic types. Gamma ray bursts are either short, less than a second, and fractions of a second, or they're long, 10 seconds up to 30 seconds, maybe up to 100 seconds. So there must be 2 different processes, 2 dominant processes that create gamma ray bursts. So perhaps there's a supernova that does it. All right. So the Hubble Space Telescope when the Swift Observatory launched and saw one, we see the Swift UVOT image there. It's like, oh, there's something, and that's in 2006. And Hubble afterglows looking for this particular one, found it, and you can actually go and hunt following up for fainter and much more distant objects. And long gamma ray bursts tend to have supernova counterparts, and that's what we see with this UV image. So they have some sort of glowing afterglow, like a supernova remnant. And that seems to be pretty common, that the longer ones have them. But if we then we go back to that one of the most massive ones ever known was Swift detected an incredible gamma ray burst, and in March 19 of 2008. And there was the left-hand side image is the UV image, and the right-hand side is an optical image as well. So what we see is that the images actually the right-hand side is the UVOT image, but what we see is that it found a gamma ray burst and swung over and saw it, and it was one of the farthest objects that could ever be seen without a telescope. Or this lasted only for about 60 seconds or 30 seconds or so. And when it got to its brightest, this object, it got so bright that if you were looking in that direction with your eye, and you were in a dark sky with no clouds, you could have seen a bright point of light just appear, not bright, very dim, just on the boundary of visibility. If you were up in a dark location like the Grand Canyon or Cherry Springs State Park, or any other really true dark locations, you would have seen a new star appear and disappear 30 seconds later, and you might have thought it's a meteor or something. Well, a very dim meteor. And the magnitude, it stayed bright as magnitude 9 for about 60 seconds, and later follow-ups on this thing showed it had a redshift of 0.937. That meant its distance was 7.5 billion light years, and anything that can be seen naked eye from that far away means it was about 2.5 million times brighter than a supernova. This is just wildly bright. It's like 2.5 million times the brightness of a core collapse supernova. We've already known that these are the brightest, that outshines a host galaxy. So we now have something that outshines, we now know stars that explode, supernovae, that can outshine 100 billion stars, and this is 2.5 million times brighter than that. So what we're doing is we're looking down the top of a gamma ray burst jet, because it can't be isotropic. That'd be too big an energy at budget. So something's got to be doing that, that's collimating it and focusing it, because that's just too bright if it's isotropic. So let's actually see what that brightness looked like. And this actually was seen with a camera, actually, and it was observed at 2 o'clock in the morning Eastern time. So if you were in Maine, you could have seen this, or if you were even down in southern New Jersey at Southern Jersey Astronomy Club in Bella Plaine State Forest, you could have seen this. So, but there's the movie that I'm showing is from a Polish group called Pie of the Sky that looks for little transient afterglows. And so what they do is they have all sky cameras, and they detected it. They got it. And later that evening, the Hubble, and it was because it was Swift, the alert went out, and in fact the Hobby Eberly telescope way out in West Texas actually was pointed at it and was able to take a redshift of that location prior to it going out. And this was the brightest object ever seen that could be seen naked eye, which is astonishing. All right, so when they get bright for a while, and sometimes we see their visible light sometimes. Well, the visible light can actually be something there, so it can happen, but it's not necessarily all in gamma rays. So gamma ray burst also has an optical counterpart that has been seen, and so there's two bits of it. The first bit is you get the gamma ray burst, and then you might get a glow of some kind, maybe what we call a hypernova glow, that happens later. And there's a bump in a bright, so there's the initial burst, and then it dims and dims, and it gets bright again, and then fades away. So there's two counterparts to some of these when we look at them through time. And in visible light, there it is. There's one that was seen in visible light with very, very faint. This is not naked eye now. And then later on, that one fading away, and we can see that they start really bright. The gamma ray burst is seen by Swift, tells everybody, and people try to follow up and do lots and lots and lots of follow-ups. Well, that's really interesting. And as people try to discover what the heck is going on, my advisor just had something very interesting that got published in August of this year, 2018. And what he was actually doing is looking at the nature of the Batsy profiles. And so he took a number of these profiles, meaning how they get bright with time. And he noticed there's kind of a triple peak to them. Frequently, there are 3 peaks that can be teased out of the data after you clean it up a bit. And so they do some smoothing of the data and find 3 peaks inside of the data. And then if you normalize those 3 peaks, you find on the right-hand image, you see the blue background, which is the actual gamma ray profile. The white overlay is the smoothing profile that they apply. And then if you then remove that and make an average out of it, a time average of it, you get the left-hand profile, which is in yellow. And there we have a bump in the beginning, a bump in the middle, and a bump at the end, which is kind of what they called it, time reversed, which is weird. It's kind of like saying, no, time is not being reversed, but however, the profile looks the same going forwards in time as it does going backwards in time. So according to the left-hand curve. The actual profile, as you can see, gets brighter and then goes dimmer. But it's very strange to think that it has this kind of wave packety sort of appearance that looks the same forwards as backwards. It's probably due to the same interaction happening on one side of the explosion as it is on the other. So we see one side of the explosion, then we see the other side. And so the triple peak thing says, oh, it's the whatever's happening on one side is happening on the other, and it's nearly symmetric. So we get this three-dimensional thing. But anyway, I just kind of scanned his article. I would invite you to go take a look at it. He published it recently in AppJ, and he's got tons of fun stuff. If you just Google time reversed gamma ray burst, you'll see it. It's all over all sorts of sites. It's a lot of fun. And it's my friend and advisor who is still going strong with this wonderful data from BATSI and Count and Gamma Ray Observatory. All right, so let's look more closely at some other gamma ray bursts. The distance measurements over time have yielded that these things can be really far away, up to 2 billion parsecs, 2 gigaparsecs, billions of light years away. So we're actually looking at things that happened in general a long time ago. Not things that seem to be happening now, because most of the gamma ray bursts are distant, not local. So it seems to be more of an ago thing than a current thing. So therefore the light is only reaching us now. And if it's 2 billion parsecs away, and it's been redshifted down to gamma ray bursts, these things are insanely energetic with what they pump out of light. All right, so the gamma ray bursts have host galaxies, which we see on the Hubble image on the right, and the Swift sort of CGR image on the left. And the Hubble Space Telescope has done numerous follow-ups and found that they're almost always in star-forming active galaxies that are extremely faint, from 2 billion to 10 billion light years away, and they're always in these tiny, misshapen, ancient galaxies that are in their formation stages. The only real exception to this is in the middle one. The green crosshairs show you where the burst has occurred, and that's also the Hubble Space Telescope went and did a follow-up too. The only different one is the one that's in the middle top, which is actually a little tiny spiral, which is relatively nearby. But all the bright dots are nothing to do with that. Those are foreground stars from the Small Magellanic Cloud. So we can see these gamma ray bursts are associated with star-forming regions, with vigorous star-forming regions, with vigorous areas where things are happening in the early universe. So what we have is a picture of a model of where these things come from. And it's called a hypernova. A hypernova is something where you have a supermassive black hole forming, but it's forming in a gaseous, dusty medium. And then there's a jet that punctures through it and disrupts this medium. So as it forms, so what we have is, so think of this as a curl that goes from the back all the way to the right, then to the black hole at the center. We start with a pretty much uniform, very low metallicity star, mostly hydrogen and helium, almost no other metals. That's very massive, maybe 40 times the mass of the Sun. It evolves extraordinarily rapidly over a course of a few million years and builds up to an iron core and then does core collapse. Now this is similar to all the other the supernova that we talked about in previous lectures. However, the core collapse, because it's a 40 solar mass star, is catastrophic and even faster than than we found when we looked at supernovae of like stars that are between 8 and 15 times the mass of the Sun. What we find is that in the center of the star, a black hole is formed immediately as the star is collapsing. And inside the core of the star, this black hole, remember the black hole is only a couple miles in diameter, which is very tiny compared to the entire size of the star, which might be it might be like 100 times or maybe 400 times the diameter of the Earth, or more like 600 times the diameter of the Earth for a 40 solar mass star. So that's an incredibly large object compared to this tiny black hole. So down in the core of the star, as material is raining on top of it, an accretion disk forms inside the black hole. Around the black hole, as material tries to fall into it, and the black hole material doesn't quite hit the center. It misses the black hole, forms a massive accretion disk with a huge magnetic field. The magnetic field makes a jet, and the jet punctures its way out of the star and rips the star apart. So this is kind of the gamma ray burst model for forming a black hole. The supermassive star collapses inside the star. While it's collapsing inside that quarter second, less than a tenth of a second, to form the black hole, form the accretion disk, and then the jet appears. The jet comes out of the center of it, punctures through the entire star, and when it does so, low energy gamma rays are created by the jet of material puncturing through and shock heating it up to millions and billions of degrees, which then emits gamma rays. These shells then go outward and outward. These are ruptured shells, and as the shells collide with other shells of gas, I mean, they're very, like, think of it as, instead of a shell, like these, not just shells, but waves of gas that are coming out. And these things, as the shock waves hit, they shock heat the other gas, and that's what forms more of the gamma rays that we see inside of the gamma ray burst. And that's what we call the prompt emission, which is the sharp spike upwards in the early part of the gamma ray burst. And then the afterglow, which is now the hypernova part of it, is that these shells then crash into the interstellar medium around that, and that creates visible light, radio light, X-ray light, and more high-energy gamma rays. So there's a very, very, very fast jet that goes and smashes into it, which creates huge amounts of gamma rays, but the waves from the jet keep going and eventually collide with the ambient medium around it and create the afterglow that we call a hypernova. So let's take a look at what that kind of looks like. It's a really interesting thing. Notice we got this stellar disk, this dusty material around, and inside the dusty area, there's the star that's in the middle. It's already gone supernova down in the core, and now the black hole has punctured through, and this jet is moving almost the speed of light. So it went out in a few seconds. Now it's going, we're looking at something that's moving almost the speed of light, puncturing through, and as the jet collides with the material directly surrounding the star that occurred as the star died, it heats the medium, causing shocks, and that shock emits huge amounts of gamma rays. And those gamma rays then, if we are looking right down the jet of these hypernova, we see a gamma ray burst. And that's where the gamma ray burst that was super bright, seen in April 27 of 2013, occurred. Now the shell that's around it is really important too. But there's the supermassive star. And again, it's all because of a black hole that has formed deep in the center, that's formed in a fraction of a second with material going around an accretion disk, and then that accretion disk creates a jet, and that jet punctures its way out of a 40 solar mass star and shreds the entire star apart as it does so. So that's the source of that massive gamma ray burst that was seen in April of 2013, and that's where it comes from. And what about these things that's interesting is that there could be things in the Milky Way that might become them, and they're called the Wolf-Rayet stars. And Wolf-Rayet stars are supermassive stars, more than 15 or 20 or even 40 times the mass of the Sun, and they have these huge, huge, huge stellar cocoons around them. And this image is from the Hubble Space Telescope of the nebula is called M167, which is the nebula surrounding the Wolf-Rayet star, WR124. So the stars at the center, the nebulas at the outside, and Wolf-Rayet stars are incredibly rare because they're incredibly large. And the stars themselves, when seen in aggregate, their spectra have ionized helium and nitrogen and carbon, and that's from the nebula as it ionizes that stuff. And then the spectra of the star itself shows very high surface enhancement of heavy elements and almost no hydrogen because that's going out into the nebula. And then there's incredible stellar winds, but the surface temperatures can be up to 200,000 Kelvin, which is hotter than which is about the surface temperature of a neutron star, and it's hotter than pretty much every other star. So these stars are going to blow up, and they'll blow up really soon. So at some point, so they only live millions of years before they explode. And then we can see that there's a few that are naked eye, such as Gamma Velorum, and then the constellation Vela. And then there's Theta Musca, which is both of these are southern constellations, and by Gamma and Theta, that means these are pretty bright stars in those constellations. gamma meaning alpha, beta, gamma. The third brightest star in the constellation Velorum is in Valoris is a Wolf-Rayet star. The most massive star is in the star-forming region 30 Doradus, is a Wolf-Rayet star as well. All right, now, did this happen nearby? Well, maybe. It's possible that Cas A, which is a supernova remnant that we talked about in supernova remnants way back in a previous lecture, could it be a gamma ray burst supernova? Remember, Cas A doesn't really have much of an optical counterpart, so maybe when it exploded, there was a hypernova, not a supernova. And we can see that there's definitely a high-velocity jet that's still occurring, that's still shredding this supernova remnant, and the right-hand side is the Hubble optical image, and the Chandra X Observatory shows evidence for a jet as well. So maybe this very recent supernova was a gamma ray burst supernova. So they might have happened in our Milky Way. All right, so that leads us to the two, we're going to now go a little crazy, but remember there were two different kinds. There were two different burst sources. And these types of things create long burst supernovae, long burst gamma ray bursts. So where's the other one come from? So the bottom one are the long bursts, where you have some sort of collapsed star. The black hole forms deep inside the supermassive star. Sometimes the collapsing star is called a collapsar. And a supernova forms, the black hole forms deep in the core, and the accretion disk forms around the black hole inside the star, and that re-shreds the entire material and then pushes everything apart, recreating a supernova. Now we call it a hypernova. And that's what we get. And that relativistic outflow that we saw in the movie, relativistic means it's getting really close to the speed of light, and then you get supernova-type remnants that occur from that long burst. However, there's another way we can create them. If we allow two neutron stars to collide, they too can do that. And a neutron star collision would last fractions of a second. So if you take two super dense neutron stars and collide them together, it makes a very, very, very high temperature disk that then explodes and creates a gamma ray burst. And here's kind of what that might look like if we have two neutron stars that are colliding together. This whole process would take less than a few milliseconds because their separation would be on the order of a few miles, and then they're also a few miles apart. And so what would be radically slowed down to exactly what it would be. And when they finally do collide, after they would create the gamma ray burst that we see, and there's the burst going outward from that particular star. And then they could be modeled with a supercomputer, and this is from the NASA visualization by Kopitz and Russell et al., so you can go check this out, and I'll provide a link later, is that the jets may actually be provided because neutron stars have incredibly strong magnetic fields. And the magnetic fields were attached. This is a computer simulation showing these two neutron stars with their embedded magnetic fields. And for a very brief time during the coalescence, a black hole forms in the center, but the magnetic field stays entrained inside of the nebula that surrounds it. That lasts literally only a quarter, like 26 milliseconds, or less than a quarter of a tenth of a second. So it's a quarter of a tenth of a second, faster than you can. It's about 3/300ths of a second, which is really fast. That's faster than you blink. So this all happens faster than you can blink, which is astonishingly fast. And so what's amazing about this, what about that short gamma ray bursts that can create neutron star collisions, is that we have actual evidence for these neutron star collisions. And one of them was actually a visual thing that occurred on August 17th of 2017. An incredibly important discovery happened on that day, and we see the afterglow of this particular supernova that occurred by the collision of two neutron stars with the Swope Supernova Survey. And on the night of discovery, on August 17th, there was a bright supernova that occurred there, and 4 days later, it was still glowing with the hypernova that surrounded it. Something happened there, something wonderful. And that's what we'll talk about next time. See you soon. Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. We're going to take a veering away from introductory astronomy significantly on this one when we talk about one of the most modern things that's occurred inside of the science of astronomy, as well as one of the most important things to happen in the last few years for all of physics and literally all of science. And it's the discovery of gravitational waves, or disturbances in space-time itself, due to the motions of extraordinarily violent collisions due to black holes. So I call this affectionately in one of my public talks, black holes and gravitational waves, the warp and woof of spacetime. If you don't know what the warp and woof of things are, you gotta go look that up. But it's also, there's, woof like a dog, so it barks in the warping of spacetime, and warp and woof for you to go look at it. In any event, let's start off with a big explosion. So on September 14th of 2015, the LIGO Observatory received a signal of two colliding black holes that collided together 1.3 billion years ago. The two black holes were about 30 times the mass of the sun. One was a little bit larger than the other, and the stars around them that you see here as they merge together, the gravitational field of these two merging black holes formed an enormous wave in space-time. And as they waved, this is going to go in loop because I'm going to talk about it a bunch of times. So as they merged together, they formed a single black hole, and the stretching and warping of space-time released 3 or so solar masses worth of energy. What you see in here, the ring around the stars, is called an Einstein ring, and the light from all the stars is being bent by the extreme gravity around them. So really that ring that you see around the two black holes, that single black hole at the end and the black holes at the beginning, is a result of stars directly behind the black hole with respect to our line of sight. And so it's not actually, the stars in the background aren't moving. That's just the path that the light takes to us from those distant stars so that we can see them. Now, this isn't actually what was seen. This was not the actual observation. This is a computer simulation showing what occurred if we were close by. If we were close by in space, there'd probably be a little bit crazier things happening there. That bending and stretching that you see there would be something that we would be part of, because that's the stretch of length and space and time itself. So it'd be it'd be like being inside a funhouse mirror and you're really being stretched and pulled. That would be kind of a violent place to be. So this is the gravitational lensing that you see there would also be something that's seen from every direction around them, but it's just our particular view from where it is. And so there's also the gravitational waves are being emitted, as you can see after it's done, the sloshing of the image as after they merge together. So during this collision, the power output in gravitational waves was far greater than the luminosity, all the light put out of all the stars in the entire observable universe put together. The collision of two black holes, which are only each about a couple of miles across, is actually the most powerful explosion that astronomers have ever seen aside from the universe's Big Bang. This detection was done by the LIGO Observatory on September 14th of 2015, and that signal was first seen, and eventually after looking at it, it was determined that one of the black holes was 36 times the mass of the sun, the other one was 29 times the mass of the sun, and the resulting black hole was only 62 times the mass of the sun, which suggests that the gravitational wave signal, that warping that you see, carried away 3 solar masses. So 3 solar masses was converted into wave energy propagating through space-time itself. And that is about 5 times 10 to the 47th joules of energy, if you really must think that. But really, it's just an enormous thing. All right, what's interesting though is that because they're waves that propagate outward from this black hole, you could actually think of them as having a frequency and a pitch. And in fact, their frequency and pitch is actually such that they would be audible in the human spectrum. So what we're seeing here is the actual pitch perspective of how fast it went, each of these two black holes went along as time went on, and you see that they, from left-hand side, you see the signal themselves, and the signal rises out of the background. And if you go check it out on the LIGO website, you see that it has a whoop 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 sound, which is really kind of fun. And this shows the actual appearance of the signal and how long it took to do the collision. So the simulation in the past was very, very, very wrong in terms of its time frame. The signal itself in that final collision took less than a tenth of a second. As a result of this discovery, and notice there's two indications, one from LIGO at Hanford, one from LIGO at Livingston, and you can see the frequencies in hertz are those of human audio, human ears. But they were really quiet. They were so very, very, very quiet, but yet they would have been audible had they been louder and closer. That's a weird thought. And so they're called chirps, because they go up at the end, like rip, like that. That's how they sound. They sound like rip as they come through. This discovery led to the Nobel Prize in Physics in 2017. So the LIGO Observatory, the LIGO, which is the Laser Interferometer Gravitational-Wave Observatory, or LIGO, involved over 1,000 people, roughly 1,200 researchers in about 20 countries. And this whole project took about 50 years from its first idea till the discovery. And the Nobel Prize laureates, which were each incredibly important to the creation of this, were Rainer Weiss, and the other half was to Barry Barish and Kip Thorne. And these three people were the main leaders in creating and developing the LIGO-Virgo collaboration, which observed the creation of the detector as well as the final observation of them. And so I provide that web link on the Nobel Prize for you to go look at. And this actually began kind of back in the 1970s, after Rainer Weiss did analyze some possible sources for background noises that could disturb measurements of gravitational waves. And so he had eventually designed a detector of some kind, and actually he presented it to Barry Barish and Kip Thorne, and Kip Thorne thought, well, I just wrote a big book on gravitation with Misner, Thorne, and Wheeler, which is one of the key books of general relativity. And in that book, he said gravitational waves will never be observed because you can't make an instrument sensitive enough. Well, it's interesting to write the book that says it can't be done and then go out and do it, isn't it? That's exactly what Kip Thorne did. He became one of the most important people in it because he said, well, wait a second, that's what I wrote. So he, of course, added a chapter later on and revised his book. So this is a laser-based interferometer, and that could overcome the noise. And Kip Thorne and Rainer Weiss were early on convinced that it could be done, and so they pushed it through to one of the largest projects that's ever been funded by the National Science Foundation in the United States' history. So where did this come from? All right, why do we think there's gravitational waves? Well, the first thing we have to remember is that gravitational waves are a result of a new way of thinking about gravity. Gravity, as thought by Newton, was very different than we think about it today. Newton, and the key thing is that Newton's formulation of gravity says that the force due to gravity propagates instantaneously throughout the cosmos. It only depends on the masses of the two things gravitating and their distance. It has nothing to do with time in the force in his equations. However, the reformulation of gravity in terms of space-time meant that time itself was part of the equation, and so therefore disturbances or changes in the locations of masses or their distributions will cause changes in the gravitational field, and those changes propagate out at the speed of light. So what's the equivalence principle? And where did this all come from? The concept that Einstein had about the nature of gravity came about from the equivalence principle. He first developed the concept of special relativity in 1905 with the idea that all laws of physics are the same no matter how they move with respect to each other. No matter how they're moving, all laws of physics are the same. That means every law of physics, including quantum dynamics, electricity and magnetism, Galilean relativity, a Newtonian mechanics are all the same for what he called an inertial observer. An inertial observer is somebody that's inside a box, inside a reference frame, inside a room with lots of sticks to do measurements and clocks to do measurements of time. And that's how you do your measurements of time and space. And either you're in free fall, such as the description, such as the little cartoon in the lower left, or you're floating, and so you can't tell if you're floating, which is the lower left, or if you're in free fall, like the lower right, you still can't tell if you're floating in space or in free fall. They're the same thing. There's no way to tell whether or not they're the same thing. Or you could be moving at a uniform speed. Now, if you look in the upper right, that's not a uniform speed because the engines are on. So let's say you are floating in space and moving to the left really fast at half the speed of light or something like that. Or you're driving down the highway at about 80 miles an hour and there's no turns or twists, and maybe it's out in Wyoming or something like that where you can drive for 30 miles and you don't hit anything. So either you're moving with a uniform speed or you're in free fall. You can't tell if you're floating or standing still. Or you're moving in, or you're falling in a uniform gravitational field. There's no way to tell any of these apart. So general relativity says you extend the concept of special relativity to include gravity as a fundamental interaction that's relative to the observer. And so Newtonian gravity said that there was a force between two masses that acts instantly. But now we can think of it instead as you're falling into the shape of space-time. So the reason the guy in the lower right is falling is because that's the shape of space-time. He follows the lay of space-time. So mass tells space-time how to curve, and then matter follows that curvature. That's what we mean by, that's what the end result of the equivalence principle is. In addition, where gravity then comes in is that in the up top two cartoons, we see a person standing on the Earth experiencing 1 g of gravity, which is 9.8 meters per second squared of acceleration downwards. Or you could be in a rocket out in space where the rockets are pushing you from below at 9.8 meters per second squared with a thrust, a force, due to the rocket engines at 9.8 meters per second squared. Now, of course, one person's on Earth and one person's in a rocket, but everything else, all other things being equal, will be equal, meaning every other experiment will be on a rocket will behave just as though you're dropping something off of a table. So if you had a table and push something off, it would fall downward and accelerate down to the ground, just as if you were on Earth. And if you were on Earth, and he threw something up in the air, it would fall back down. And that's exactly what would happen inside a rocket. So you can't tell the difference of any kind of acceleration. You can't tell the difference between the acceleration due to gravity and the acceleration due to any other force, such as a rocket or something like that, or being pulled up very rapidly by a cable. And that's what the equivalence principle says, is that not only are the physical laws the same no matter how you move with respect to each other, but it also says that you can't tell the difference between your inertial mass and your gravitational mass. They are the same thing. So Newton's mass that he derived from his laws of motion and his definition of inertia then becomes the thing that is inside of gravity itself. And so this concept of mass then is that mass affects space-time, and in fact warps it and changes its geometry such that other masses obey the geometric shape that has been put down by a bigger mass. So that's what the essentials of this equivalence principle are. And so when we think about what we mean by this move, we then say things gotta move, right? So how do you know if things move? Well, you need a meter stick or some sort of measuring tape or some way of measuring distance. And so that distance measurement is incredibly important. But you also have to, in order to say how things are moving, that says things have got to take time to get here from there. So time is an element too, and so speed and time are important. So when you integrate them all, you have to say, well, why do things fall? They follow the shortest possible path in space-time. That's what they do. And that shortest possible path, its length is called a metric. And the metric is the thing that combines space and time together such that you can say it has to take the shortest possible path in space and time, which is an interesting concept. So now we're going to get into the meat and bones. I talked about this in my general relativity lectures, but I'll give little tiny bits here because, you know, what the heck, here we go. In the upper right-hand area, we see the equation, which is the Schwarzschild metric for a weak gravitational field, such as around the edge of the sun or at the surface of the Earth. So the left-hand side of that little ds squared, is the path length in space-time squared, just like Pythagorean theorem. We take the square of one side and square the other side, and the hypotenuse, that's where that's really coming from in essence, is equal to, there's some factor that involves Newton's gravitational constant g, and the mass m, and the distance r, and the speed of light squared, and you take that thing in parentheses and multiply it by the speed of light squared and multiply it by a length of time squared. So that's the time length that we're going. And then you do that same little thing, but instead of minusing it, you plus it, and you have little dr squared, which is height above. So we're assuming a spherical thing like an Earth, and how high we are above the Earth is dr. That's its altitude above the surface, or above the center of the mass, or that's a good way of talking about it. And the d omega squared, r squared, d omega squared is like left and right. But we're only worried about up and down for that metric. And that's the gravitational metric, or for a weak gravitational field, we are going up or down inside of a gravitational field. Now, we can reformulate. There are many ways you can actually make a metric and measure the length in space-time. It depends on the conditions. The metric at the top shows what it's like near something like the Earth or the Sun. But if you now take some two big black holes and smash them together, they're going to affect space-time in a very strange way. But very, very, very far away from those two black holes, when they collide, that wave that happened will diminish as space-time, as they progress through space-time, because they spread out. So as the waves spread out through space, as they progress, as they travel away from the event that created them, they spread out and get weaker and weaker and weaker. In fact, they get so weak that they almost get to the point where they're just tiny bumps in front of flat space. So flat space, we get rid of the 1 minus gm on the top and the 1 plus 2 gm over r squared thing at the top, and we're left with almost the thing in the middle that I show, which is now a path length ds squared, and there's no effect on time from gravitational waves, but there is a stretching to the left and there is a stretching to the right as the waves travel up dz. So x is left and right, dy may be forward and backward, and z is up and down. So as the wave travels from the top to the bottom, it'll affect things going left and right and forward and back. And that's what those little h's stand for, is the tiny, tiny, tiny bumps and deviations that occur to flat space-time very far from a gravitational wave source. And so we can model, since it's a wave and it's periodic, we can approximate, we can take as our first guess that the little tiny h's will be functions of time, just like a sine wave. And so a sine wave is just a very simple water wave, or sine waves are just a way of, if a sine wave can be best thought of as just a simple oscillator that goes up and down, and as you watch it go back and forth in time, take a spring, like a weight at the end of a spring, and lift it up, and then traverse it, and then carry that spring as it's going up and down off to the right. Now, if you're smart, you do this in a dark room, and then what you do is you have a light. The bob at the end is a light, so it goes up and down, and and as you walk this thing, there'll be a wave type pattern that goes up and down, and you'll see that, and what you see as it travels will be a sine wave. And that's described by the amplitude A times the sine, which is the sine of how fast the frequency of the wave W, times the time that it goes, and so as you move, minus z, which is, a little bit off from where you started. So that's the phase angle difference of that. So that gives you some periodic variation in the lump of space-time. And by small, I mean really small. 1 part in, say, 10 to the 21st. There's very, very, very few things that we ever measure that are that small, because when we think of dollars and cents, we only think of like 1 penny, which is 1/100th, or 10 to the 1 part in 10 to the second. Even if we think of things like trillions of dollars, we're only thinking of 10 to the 12th. Like $1 out of a trillion is only 1 part out of 10 to the 12th. But this is 10 to the 21st. And that's getting really hard to measure what that really means. So it's tiny. It's extremely tiny is a good way of thinking about it. Another way to think about it is that the size of an atom is about 10 to the minus 10th meters. That's the size of an atom. And what would be 10 to the 11th meters? Well, that would be something extremely big. That would be 10 to the 11th, 10 to the 8th kilometers. 10 to the 8th kilometers is about a light second away. Well, it's about 1,000 light seconds away. So that is well past the moon. So we're talking the diameter of actually it would be much past the moon, be out past Mars. So 10 to the 8th kilometers, not 10 to the 5th. So it would be 1,000 times further out past to the orbit of Mars. So something compared the diameter of an atom compared to the distance to Mars. That's that's on the order of 10 to the 21st of a different size scale. So this is a tiny, tiny, tiny change. So we're not expecting to see a funhouse mirror far from the event. So how do they move? And this is even more math. I'm sorry, but you got to take it because it's your medicine today. And the upper right-hand corner, we're showing that little tiny, tiny, tiny equation which shows the bumps. So I made the equation really tiny. But we can take pieces of that equation, the right-hand side, and then we see this equation that we have at the top is called the geodesic equation. And that geodesic equation looks at variations in time, variations in space, and shows the product of their variation of space, of time and space, and compared to the acceleration of these things. And that variation is called the geodesic, and it says how do things vary as things propagate through. What are some symmetries to the space-time? How will things move? So the geodesic equation, if you plug things in, will show you how things move given a metric. So that'll show you the shortest paths. So plugging this stuff into that equation gives you the shortest paths. But the changes that the metric shows are so incredibly tiny that there are literally almost no changes to the geodesic, meaning there are no path changes in terms of the coordinate changes. So it doesn't push things across coordinate lines. It stretches the sizes, but it doesn't change the coordinates of anything. It's kind of a weird thought, meaning that the changes are so incredibly tiny, you can't actually see it doesn't push it across the tick marks of a ruler. So at tick marks of a ruler, whatever's being pushed don't get pushed across those tick marks. So you can't measure the change with the coordinates. However, there is a distance change, because once you add up all of the tiny pieces of the change as time progresses, then there is a distance change across a very, very large section. So while there's no coordinate system change, there's an actual length change, because the coordinates themselves get stretched and pulled, meaning this is weird, meaning the ruler itself gets stretched and pulled and squished and pulled as things progress. So you can't tell if there is a change, but there is a length change. And so that length change is called the strain. And that length change, we're calling it the little bitty tiny delta length of t as a function of the real length, which is the average change. And that's proportional to that sine wave we thought. And so we have, that last bit is called the strain, which is how far is the length being changed. And this is the thing that when people say what we're talking about, this is what, when they say, oh, it's this, when we're going to talk about, oh, it got shifted by this much. This is what we mean. These are the equations that we had, is looking at the actual length changes or path length that was done. So even though there wasn't a coordinate change, the coordinates themselves, the meter sticks themselves get stretched. So you can't do this with just 1 meter stick. So you have to have something that can detect a change, a relative change in distance to on the order of 10 to the minus 21st. So that's kind of small, and that's equivalent to saying, so again, let's give another good analogy. If you look at one of the little hairs that from your head that might have fallen to your desk while you've been listening to this and nodding off, but your hair might have fallen to the desk, and the width of your hair, that's very small. But imagine comparing that to the distance to the nearest star, Proxima Centauri. The width of a human hair is about a tenth of a millimeter. The distance to Proxima Centauri is about 4 times 10 to the 13th kilometers, or 4 times 10 to the 16th meters, or 4 times 10 to the 19th millimeters. So this is an enormous change. And so if you could somehow measure something, if you could measure the accuracy of the distance between the Earth and the nearest star to the accuracy of the width of one human hair, you'd have done a pretty good job. So that's what was done. That's why they got the Nobel Prize, and that's why it took 50 years to do. So let's see how they did it. All right, so they have gravitational-wave observatories. These were built. They took a huge amount of funding and money, and they were by the National Science Foundation. And the 2 observatories that were built, each of them has 2 long rulers, and you compare and contrast the strain difference between the 2 of the rulers, and they change with time. And they change with time in a very peculiar way. And so what we're doing is each of the lengths of each of the arms of this interferometer, which are the long things that stretch away from the central building, those things are about 4 kilometers long. And so if the length that they're bouncing things off of, the length that they're measuring is 4 kilometers, then they have to measure something that's smaller than the width of a proton, which is 10 to the minus 18th meters. A proton is about 10 to the minus 15th meters, so we're looking at the shift of something that is being shifted only 1,000th of a proton. And so you have to build something pretty accurate to do. So what exactly are they looking for? They're looking for interference patterns in waves. So what do we mean by interference patterns? So you take 2 rocks and throw them into water like this, and you get waves rippling out on the surface of the water. And if we look closely at the places where where the 2 waves meet, they combine and get higher, and that is called a constructive interference. And that's where we see it brighter and higher because it's reflecting sunlight. And then between the waves at the dips, it looks darker because of destructive interference as the waves go flat. So the waves pass through each other. One is positive, they cancel each other out because the trough of one wave meets the peak of the other, and when that happens, they cancel each other out and they're flat. And that's called destructive interference. So we're going to look for, in some way, constructive and destructive interference as the waves pass by and change the lengths of these rulers that we've built in these 2 locations. So what kind of waves are we looking for? They're not water waves. They're really weird looking waves. These are the kind of waves that we're looking for. Notice they do have a sinusoidal variation, meaning they go fast when they're in the circular form, and they go out to the edge and they slow down. But there's 2 polarizations to these waves, and both of them are demonstrated here. One of them is called cross polarization, or X polarization, that's on the left, and the other is called plus polarization, or just plus polarization, on the right. And these waves are affecting test particles as they pass through. So these dots are like test particles that are being affected by a traveling gravitational wave. That wave is coming out of the screen towards you, and that's what's happening, or into the screen from you. So they're coming perpendicular to the screen as you're watching this video, and this is how the stretching occurs. So notice if you have a combination of these things, it stretches it in one direction and squishes it in the other. And if you build, and they're right, and each of these stretchings and squishings is right angles to each other, right? So since they're not like 45 degrees in either the plus or the cross, the squishings are perpendicular to each other. Now, I said this is like going into the screen or out of the screen, but let's look at it from the side and make it look really pretty. So this is what it would kind of look like if you could visualize a gravitational wave passing from, say, the from the upper right of this image all the way to the lower left. It's a very strange sort of tube-like, worm-like shape. So you can see that the squishing, look at any individual circle or squished ring, the wave propagates along the tube. And so these waves propagate in this manner. It's not that they get fatter and thinner. They're getting squished and stretched as they go. You can follow any individual one of the hoops, and it's behaving exactly like I showed you before, but they behave sequentially, and that's the wave-like behavior we're talking about. The speed of the propagation of that wave, we're slowing it down really massively, of course, because it propagates at the speed of light. So this is the propagation effect of gravity through space. So when any massive object or any object changes its position, well, it has to be super massive in order to make massive gravitational waves. But these and they move fast enough so that things can kind of rearrange with each other more quickly. But a very massive gravitational wave event, some sort of alteration in spacetime, will cause all of spacetime to do this as the waves propagate outward. And this is the method by which they propagate. Remember, we talked that Newton said that the force due to gravity, not a force anymore, but the shape of spacetime, the shape of the force due to gravity was Newton thought of only depended on the masses and the distance. However, Einstein said it took time for the change in gravity to affect something distant. So the concept of gravitational waves comes way back from Einstein's thinking, but he didn't think there was any way to ever measure it, or even if it was real. He just thought it was probably just, it wasn't real, that it was a coordinate thing, and it was just something that would be worked out. But it ended up being that, yes, there is an actual stretching and squishing, and length actually does change while the coordinates don't change. And what do we mean by coordinates again, that the coordinates are not changing? Notice how the hoops are not getting near, well, they're kind of getting stretched and squished along each other. But see the little lines that connect them to kind of demonstrate that's kind of this wormy pattern? You notice that there's not more worm pattern lines being inserted or created. They're the same number of worm lines. I'm just calling them worm lines. But they're the same number of lines, and those lines are the coordinates. So you can say that how many, on the far left-hand side, you say, well, how many coordinate, say, worm lines are there around? And I guess to my eye, I count 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 steps around. We can think of eight pegs connecting each ring to each oscillating ring. So you don't increase the total number of steps. The size of the steps themselves change, and that is the stretching and squishing of spacetime. So the geodesic itself is the measurement of the change of the metric, but because of the tininess of the change, this is not a change in coordinates because there's still 8 steps. It doesn't grow to be like 10 steps. See how the ring doesn't grow and there's all of a sudden 10 steps? No, it stays 8 steps around a ring, especially that end ring on the left. So that's what we meant by the coordinate system is staying the same, but the length is changing. So notice the stretching of the lines between them, how they're actually oscillating. That is definitively a change in length as the oscillations go and propagate through. All right, so that's the propagation of a wave and what their shape is. So how do you measure this thing? Well, you use what's called a laser interferometer. And a laser interferometer takes a laser source, it shines it at a half-silvered mirror, so half the laser can propagate through the half-silvered mirror, and the other half can get reflected. Then the wave of light goes down and bounces off of a very steady target that doesn't move, and then the two beams then come back together and then recombine after one passes through the mirror and the other passes along it. And then if a wave propagates through, then the actual length of the arms changes with time. And you can see that the arms are getting squished and stretched, and the waves then themselves are either in or out of phase. If they're in phase, they constructively interfere and make a little bright light, and if they're out of phase, they destructively interfere. So as the arms change, you get a flicker. And that flickering of the light that we saw in the original thing, that chirping, is what was seen. So it basically saw lots of background static. Maybe the light was just shimmering a little bit. And then all of a sudden it went whoop. And there were just like a really, really, really fast change where it vibrated very, very, very quickly. And the lengths of the two arms, one got shook really hard and the other one got shook in the other direction. So what's being measured then is a time difference in the paths, and that's how the length works. Is that even though the coordinate distance has not changed, since the path length has changed and light has the same speed, then there is a time difference, and that's why the waves can be in and out of phase, and then create the interference pattern that we see. So there's a laser beam. The thing in the middle is called a beam splitter, and when this interference pattern, it passes them together, and that's why this is called a laser interferometer, because we measure the interference pattern as something affects one of the arms of the interferometer. So again, the ability to do this was scaled up over the course of about 20 years to be able to measure the width of something that's 1,000, a shake that was only the 1,000th of the size of a proton. So how big is a proton? So what a bunch of wonderful people did is they created this was created by T-Pile at Caltech to show you the exact size of a proton and exactly how big the shake was. So now we're down by that blue thing, and that's a proton at 10 to the minus 17th meters. So the tiny shake was 4 times 10 to the minus 18th meters. This shake is so small that if the proton were a ball, you couldn't see. It would be like walking on the surface of the Earth. You can see the curvature of the Earth. The proton is so big compared to the size scale of the shaking or the movement due to it, that actually the wave would see a flat surface as it pushed it across. So this is an amazing, amazing concept, that there's the electron zipping around a hydrogen atom. And so the center of a hydrogen atom is a single proton down to below 10 to the minus 15th meters, 16th, 17th, and 18th meters. And as the gravitational wave passed through, that's the shake that it did, and that created the tiny, tiny whip that came back and forth. That's why it took 50 years, and that's why Kip Thorne didn't think you could actually see it, because this is a very tiny effect. It's extremely tiny. So let's see exactly what the places are that we're able to actually see this effect, these gravitational waves that did this. So there are currently only a few gravitational waves in existence in the world. And there's the LIGO group, which has 2 observatories, one in Hanford, Washington, the other in Livingston, Louisiana. There's the GEO 600 and the Virgo collaboration, which is now online. This was an old slide, which is in Southern Europe. And then there's the approaching the Kamioka gravitational wave detector, KAGRA, which is going to be coming online pretty soon. Should be online now. In fact, it is. And then there's one there's LIGO in India. The Indian government broke ground starting in 2016 to start beginning it. So there literally are only 4 active gravitational wave observatories today, with KAGRA coming online pretty soon. So you have these things, and that's what's detected it. They're very expensive to build. They're extraordinary. They take extraordinary technological achievement in order to do, and they take a dedicated funding source as well as governmental support. These cannot be done by private investors in any way. So this is your tax dollars discovering the fundamental aspects of the cosmos. That's really what's happening for U.S. citizens listening to this in this video. So let's look at some of the observatories. This is LIGO Livingston, and you can see the main facility in the middle and the two arms, one stretching to the north and one stretching to the west, and there's an access road there. They put this in Louisiana because they found a place where there's not a lot of people around. That was part of the goal, and they want to make sure nobody's going to come up to it and mess with it. Even still, they have, in some public talks that they've saw, that the Livingston detector, they've had to do some repairs because some people come on up there and they think, hey, that looks like something fun to shoot. So they've actually repaired some damage to the sides of it due to entertaining people that hit it with a shotgun. So that's actually been done. In any event, they now encase this whole thing in concrete, and there's a big moat around it, lots of high energy, lots of high fences with barbed wire, and so they got a lot of security there too, whatever. In any event, it has to be secure, and it has to be very, very far from where things are really happening. So Louisiana's got a bunch of alligators, and they take it offline whenever there's a hurricane. All right, so the other one is in some place that literally nobody goes to. This is in Hanford in eastern Washington. And this area of eastern Washington was a nuclear bomb test facility. So it's one of the most radioactive locations in the United States, other than the Trinity site and some radioactive dump zones near reactors. And so what we see is one of the chambers going off to the left, above, and one going to the right, one to the left and one above. And each of the lengths of these arms is about 4 kilometers, so these are perspective views, and those are incredibly long arms. The detectors are so incredibly sensitive, remember they have to be able to see the motion of a proton, that at LIGO Hanford, they're able to detect when the tumbleweeds hit the outside, because they actually have to go clean the tumbleweeds off of this thing, because it is the upper desert. So tumbleweeds will come and they'll hit the side of the thing, and when there's a big wind, lots of tumbleweeds hit, and they go, what the heck is that? And they get a signal, and it ends up that tumbleweeds have been hitting it. They also can detect when Jupiter is in the sky and when it's below the horizon. They can also detect when big trucks are driving on the highway about 10 miles away. And they can also detect when there's building demolition in a nearby city. So that's how sensitive they are. So they have to continuously model what they see as noise, because background noise can be something like clouds going overhead, or rain, or somebody walking into the facility and dropping their keys on their desk. It's really quite that sensitive. So when people go into these facilities, it's a quiet zone, and things got to be really clean. Can't be no hoarders in these places, because you can't have things falling down. So it's a mess. There's very little mess in these environments, and when they do have that kind of mess, they try to eliminate all those messes. In any event, nothing falls, or at least try not to make things fall in there, because it can cause a signal. And that's what I heard from many of the other researchers. And there's amazing talks if you go to TED and look for them. So here's the inside of where the two beams meet. The laser beams meet is where the interferometer beams meet. You can see a tube on the right-hand side going down that goes out one arm, and a tube going up to the left, and that's the other arm. And in the center is where the beam splitter is, and where the detector and where the interferometer detector is. And here's a worker looking over one of the beams, one of the beam tubes as it goes out. And you can see that they try to keep it clean. They try to keep as many things as they can. And hair dropping on the floor is kind of important, because you don't want your hair getting inside those tubes, because it has to be insanely clean inside the laser tubes. So these are 4-kilometer laser tubes that must be evacuated and made to a perfect vacuum, or at least as best as they can. So they try to keep them wildly clean, clean room clean, so there's no dust to reflect off of, in order to make fake interference patterns. So you have to go in with clean hands and make sure you have a mask on so you don't breathe stuff out, and get moisture inside there as much as you can. And then when they evacuate it, they have to make sure the temperature and humidity is just right, and they check for dust particulates and so forth. So when they're actually installing these things, they have to, one of the biggest concern is cleanliness inside of the tubes themselves. Well, what's at the ends of the tubes? At the far ends of the tubes are these wonderful mirrors, because it's lasers. So the mirrors have to be really quite perfect. And so they have to be prepared in such a way that the mirrors are incredibly flat. The material out of which they're made is almost completely pure, so there's no imperfections in them as much as possible, in order to assure that the laser bounces correctly, as well as that there's no imperfections that lead to strange mass distributions or wagging of it because you don't want, you have to have a macroscopic thing, so the measurement of it has to be very accurate. You don't want it to be out of balance in any way. That includes its chemical composition as well as its surface as well. So once these things get installed, they kind of look like this, and this is just before sealing up the end of the chamber, at the very far end where the mass would be reflected off of. And so this will be inside its own chamber, and this chamber will then be the target of the laser, and it will be reflected off of this surface. And the mirrors are, well, the only way you can actually see this thing is because the light is being reflected off of at some glancing angle. And without that, these optical surfaces have to be nearly perfect in their surfaces as well as their chemical composition. So that's the only way you can actually see them, is that there's a side reflection. Otherwise, you wouldn't be able to look directly at the surface. But now once we look more carefully, we can say, well, how do they actually do what they're doing? And they call these mirrors test masses. So the test mass is the thing that they're seeing if it's moving away or towards. Now the arm is the length of the laser beam, and so the length of the laser beam goes from where the laser comes out of the beam splitter, and then hits this test mass, and the test mass reflects the laser back to the beam splitter. And what they've done is that there's multiple layers to the entire system. And in fact, there's 4 layers in a quad suspension system. And if you look at the little graphic that I have there, you can try this at home. Take 4 equal lengths of string and put like a little fob, say like a bunch of locks or something, like combination locks. So tie some combination locks together on a series of strings like this. And in fact, probably nothing that can swing. You don't want any other additional swinging. So you want something like maybe, I don't know, something that's not going to provide extra swings to them. Maybe billiard balls or something. Tape some string to these billiard balls. Tape it down really hard. Wrap it up tight, and then put them together. Now hang them in this way, and then shake your hand back and forth rapidly, just back and forth in a little quick motion. The bottom one will move almost not at all. These quad suspension systems are used in extremely, really expensive cars like Maybachs to give you these incredible rides that are very smooth. So the better your suspension system, the more independent motions where waves can be dampened, the better. So I invite you to kind of try this at home with 4 separate things and just shake it fast. Now, of course, if you move it slowly, the whole thing's going to, of course, move. But if you just give it a pulse at the top, left or right, or back and forth, but not up and down, but either to side, then the bottom one won't move at all because the others above it will take up the slack. And so each of these mirrors weighs about 40 kilograms. And at the top, they're held by silica glass fibers, and these fibers are the things that connect them. So these tiny, tiny thread-like, very strong fibers that don't transmit any more of the vibration through them. And so there's another look at what one of the test masses look like in the beam splitter chamber. All right, so once they do that, then they put it all together and they've split the beam and they've reflected off of it and look for the signals. Here's what the test signals look like. This was the actual timing and profile of the signals that they looked for and observed. So at the bottom was a frequency spectrum to show what the frequency of the wave was as a function of time at the 2 locations, Hanford and Livingston. And this was what was seen for the first gravitational detection. Now what we can see is that there is actually there's an observational frame, which is at the top, and then the bottom one is a simulation. The middle frame is numerical relativity, meaning you don't just want to do this. You want to know that you're actually going to get something done. So one of Kip Thorne's major contributions to this was to promote the theoretical understanding of how these gravitational waves would look. So if you collide this thing together and smash that thing together, smash two black holes together, maybe one's bigger than the other, maybe one's smaller than the other, maybe they have spins, maybe they have an elliptical orbit, etc., etc. And you make huge computer simulations, and that's called numerical relativity. And when you put them together and say, well, this is what it should look like, you make a whole bunch of waveforms, and you do that in advance, very far in advance. And then once you get a signal, you check it. You say, oh, it's like one of those signals. Or it's not like one of those signals. So tumbleweeds hitting the surface of it will not make this kind of signal. A plane flying overhead will not make a signal that looks like this. Only two colliding black holes made a signal like this. And the residual, which is the third frame down from the top, is the background noise they had to eliminate. So the background noise could be like planes, clouds, dust, somebody's cat meowing 10 miles away. It could be a lot of different things. And notice that the two waveforms, and here was the thing that convinced them, is that the two observations, the one in Hanford and the one in Livingston, were measured at almost exactly the same time. Almost exactly the same time. The difference between the measurements of Hanford and Livingston, Louisiana, was their light travel time between the two locations. So if you shone a laser from Hanford, Washington to Livingston, Louisiana, and you would say, how long does it take for light to get from there to there? That was the time delay that was seen between the two signals. So that's how they knew they came from the same exact source. And they noticed the chirp signal is nearly identical. In fact, it's for all practical intents identical. And both of them saw the same event, the same time frame, and everything. So that's how they knew that this was the same thing. Now, they made the observation in September, and I remember that Christmas time, I actually visited my family. My mother and father live in Brownsville, Texas, and one of the research groups is at Brownsville, Texas, University of Texas at Brownsville. So I went and visited a couple of people there who I know, Joe Romano and Matt Benquista, who were on faculty at UTB at the time. I think Joe's moved on, but I think Matt's still there. He might still be. I forgot. I didn't bother to check before saying this. But anyway, at the time, they were there, and I visited, and only 3 months prior, this gravitational wave signal had been detected, and they'd been running all sorts of simulations and checks, and they've been checking it like mad. They've been in the middle of their checks, and I went in and I said, hey, I think this gravitational wave stuff is really cool, and I want to give public talks on it. I've given a couple public talks. And they have a gravitational wave, because since they're part of the consortium, one of the many universities, and they were 2 out of the 1,200 people that are researching it, their public relations person overheard me from the hall and said, oh, I'll get you some stuff. And she went out and got me a whole stack of posters and cards and things, and they just smiled and looked and said, this is really cool. Yeah, it's pretty big. And they just talked about, normal stuff. They talked about physics and things that they did not they didn't tell me anything. That was a bummer. They didn't tell me anything. They knew I was talking about this. They knew I put in a crazy little proposal for Watt trying to look for him in New Jersey, but whatever. That's neither here nor there. Anyway, that was kind of fun, and there's my shout out to them and their tight-lippedness, because a lot of people had to be real tight-lipped because they didn't announce it till February. Anyway, so here's what this signal's source looked like if you were to simulate what the gravitational waves in space-time were to appear to be far from the black hole at the moment of the event that happened in September, that was observed on September 14th, 2015. And it's been slowed down about 40 times. Remember, this happened over the course of like a quarter of a second. And as it did so, like 3/4 of a second was its total time. And it took about a quarter of a second for it to actually occur. So you see that the waves propagate out through space, and the space itself gets pushed in these incredible wave formats. But once it's together, it rings down into that, and the gravitational waves ripple outward in space. Notice it does this double-lobed feature, and so I went look at the early segments. In the early part, you see one going each way, like 2 arms to this. And that gives kind of what they call a quadrupole shape to the ripples. and that's part of what's being seen by the two, and so that is an expected result for gravitational waves. All right. And the only reason we're looking at this two-dimensional view is because the universe is 3 dimensions and the gravitational waves propagate out in all directions. But what we're really looking for is it's really hard to visualize going in 3 dimensions. So we pretend that we're in a fictitious 4th dimensional space looking down on this, and the waves going up and down into the blue are that. So the compression and rarefaction are the waves themselves in space-time, in our space. All right, so if we really wanted to look at it from a alien 5th dimensional being sort of thing, where 4 dimensions of space and 1 dimension of time, here we see the event here. This is a simulation showing the collision of the 2 black holes, and the surface is actually our universe viewed from some hyperdimensional, hypothetical, flat, high dimensional space in which our universe is embedded, so a 4th dimensional space. So our universe to them would look warped as a 2-dimensional sheet, because now we just remove 1/3 dimension just to make it easy to visualize. Otherwise, you have to have 3 eyes in order to see it. And around each one of the black holes, the space bends down into this crazy, crazy, crazy funnel shape. And that warps the space-time due to the black hole's enormous, enormous mass. Both of them, they have enormous mass, about 30 times the mass of the sun. And the various colors depict how time is flowing. All right, so we're going to come back to this. I hope it'll replay. I'm pretty sure I said rerun the image. I hope I did. But near the black hole, the colors depict the rate at which time flows. So as time flows normally, very good. Near the black hole, the waves in the green region, that's time flowing at a normal rate. In the yellow areas, time is slowed by 20 to 30%, and where it's red, time is almost stopped. So that's another way of looking at that, is that the flow of time is in that particular way. So the redder it is, the slower time is going. When we're looking at the nature of the arrows, those arrows depict the arrows depict how space is flowing. So when we think about the direction of the flow of space itself, we can think of exactly what the free fall rate of something is at that location. And the free fall rate at near where it's red is the arrows indicate that the rate of flow of space-time. And I described what that means in a different video when I talked about Andrew Hamilton's concept of a river of space-time, where we can think of the arrows as flowing towards mass. And so space can be thought of as flowing, and the bigger the arrow, the greater the flow of space-time. And so you can even see that space-time itself is being warped and changed, because as they orbit each other, space itself is being dragged around, and the arrows show the direction of the dragging around. And the waveform that is created by these two things, the simulated wave flow. So we have a numerical simulation that shows the wave pattern, and then we also have the numerical simulation that gives rise to the visualization as well. And the blue area on the outside shows the propagation of those things. So just before the 2 black holes collide, as they're merging, we slow down the rate of the movie rapidly, and we see that there's these enormous bucklings and shiftings of space-time. As space-time itself gets warped radically, some of the greatest warpage of space-time since the Big Bang, and in that warping, 3 times the mass of the sun is taken away from the black holes to create the waves that you see propagating outward. So we can think of that as the most incredible storm that's ever been seen. And it's more like a space-time storm as the fabric of space and time, the warping. And now, as you heard, that space-time has sounds, the woof of space-time, as the warp and woof of space-time has an enormous storm, like a crack of a whip or a chirp as they go out. If you were close to this, you wouldn't survive. This close, you'd be dead. So again, the course was all about million ways to die, and this is an incredibly bizarre way of going. So one more time, seeing it get slower and slower, and the arrow of space-time flows faster and faster towards it, and time itself slows down, and the warping in the physical dimension of space gets now rebent in multiple ways, curved back upon itself, not just anti-gravitationally. See, up is like anti-gravitationally, and then away. So this is a strong stretch in terms of space and time as mass is converted into gravitational waves. All right, so what does that look like here? This is interesting. So as the gravitational wave passed through the Earth, this is a really funny little animation made by Dr. Hurd at Caltech at MIT in the LIGO lab. We see that the Earth actually gets stretched and squished. That's an extraordinarily exaggerated view, of course, because we know that the stretching and squishing was only about the size of 1,000th the size of a proton, so yeah, that's not it. However, if the Earth were much closer, that would occur. If the Earth were within less than a light year, this would be what would happen. So that's kind of a really wonderful thing to think, that some things that this close got affected in this way. I think that would cause a few earthquakes, a few maybe, yeah. It would also cause, your milk to fall off your table. Okay, so where did it happen in the sky? When the gravitational waves were detected, the funny thing is that because it's just two of them, they can only detect roughly where they are in the sky. And so because they were only detected by the two detectors, this is as best they got. These oval-like banana shapes are a result of the location of the timing between the two, Hanford and Livingston, as well as the most probable areas get brighter and brighter and greener and greener. So the inner circuit, the inner yellow line is where they're 10% confident where it is, and the purple line is they're 90% confident that it was inside that purple area. And so you can get tighter and tighter and tighter in and say, maybe that's it. So it could be from the Magellanic Cloud. Nobody knows. But it had to have been much, much further than that. Because where these things occurred is that because of the waveforms and how quiet they are, the measurement of the waveforms said that they were approximately 1.3 billion light years away. Because the gravitational waves travel at the speed of light, that's how far they go. So this was the first detection of gravitational waves by anybody in the entire history of the world, and it won them the Nobel Prize for this discovery, for two black holes that collided 1.3 billion years ago. And the light and the signal from it arrived here on September of 2015. Now, what we find is that there are more ways that gravitational waves can be made, other than this. There are many ways gravitational waves can be made, and that's just one of them. Colliding black holes are one. And the most important thing about gravitational waves was discovered extremely recently, and that's coming up next time. See you soon. Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Last time we were talking about gravitational waves and their discovery. When they were discovered back in 2016, and as a culmination of over 40 to 50 years of work with the LIGO observatories being built, and the people who devised it and supported it through the decades got the Nobel Prize for the initial discoveries. Well, since the initial discovery in September of 2016, there have been a grand total of 6 other, as of this particular time, 6 other gravitational wave sightings that have occurred, and we're going to talk about the most recent of those. The last one that was discovered and it's the most important. So again, we're looking at the gravitational wave spectrum, and the spectrum here shows that gravitational waves themselves are predicted by general relativity, and the ones that are currently doable are with the terrestrial interferometers, which would arise from very rotating neutron stars that have little lumps on them, and they would make what's called star quakes. And also supernovae should be things that they see. Also, they should be able to see compact binaries, such as combining black holes, which is the dominant number. The first 5 were medium-sized black holes, meaning a few tens of solar masses as they combined. But what if 2 neutron stars collided? Neutron stars, of course, are very massive objects that have been compressed to extremely small sizes. Most neutron stars are between, say, 1 and 3 times the mass of the Sun, and that whole amount of mass has been compressed down to something a few miles or a few kilometers in diameter. They're very, very, very tiny objects. They're extraordinarily dense. And in my neutron stars video, I discussed exactly the interior structure of these neutron stars and how incredibly weird it is. But basically, there's zero space between the individual nuclei in the neutron star, and you can come up with these wild phases of matter where there are no individual nuclei, where all of a sudden the interior of a neutron star is effectively one big atomic nucleus. Importantly, neutron stars can have a property of being a pulsar. One of the important properties is as they shrink, the magnetic field of the star itself gets more intense because the material isn't going away, and the material that makes the magnetic field isn't going away. So since it's not going away, as the object shrinks, the intensity of the magnetic field increases radically. It increases so much that the magnetic field itself can accelerate particles to nearly the speed of light, and as they get ejected out the poles, and it also creates hot spots on the magnetic poles of a neutron star. And if the magnetic poles are not aligned with the spin axis, then you can have what's called a pulsar. And the beams of light that come out from a neutron star along its polar magnetic field axis, because as electrons go spiral in the magnetic field at nearly the speed of light, they emit synchrotron radiation in radio, as well as X-ray light, and we see these as X-ray or gamma ray pulsars. So a pulsar is an incredibly important element of the neutron star experience. And as pulsars spin down or get slower and slower, they fade away. So we should expect to see a large number of neutron stars throughout our Milky Way. And their effects are very important, as we'll see soon. Back in 1974, Russell Allen Hulse and Joseph Houghton Taylor discovered a binary pulsar, 2 neutron stars orbiting each other, both of them pulsars, and their discovery earned them the Nobel Prize in Physics in 1993 for a reason we'll discuss, and that's subject of this video, and the same thing in just a second. It's called the Hulse and Taylor pulsar binary, and each of these neutron stars, the initial neutron star was found to be rotating 17 times a second on its axis, and they eventually did, with follow-up observations, were able to determine that it was a binary neutron star. And they used the Arecibo Observatory that you see here, which is located in Puerto Rico. What they did that got them the Nobel Prize, though, is that since they discovered it was a binary pulsar, they timed the radio pulses for a long time and noticed that there was this incredible systematic variation in the arrival time of the pulses. They changed in a very smooth and repetitive manner, and their normal period is about 7 3/4 hours, and this variation was happening their variations in this binary, the initial binary the initial pulsar they found, had a variation that changed smoothly. And that's if it was in an orbit around another pulsar. And that's the only way they found that. So he said, oh, this thing is changing. So if it's doing that, it's just in the same way that we would find a binary star. So we might find a spectroscopic binary. And instead of finding a spectroscopic binary, we found a pulsar binary. So what they discovered by looking at the variations between them is that the pulsar they orbit each other in about 3 light seconds, with a diameter of about 3 light seconds. And that's about 2/3 the diameter of the sun. So remember, 100 Earths fit across the sun. So this would be about 60 or 70 or 60 or so Earth diameters between these two pulsars. And each of the pulsars is about the size of a big island, such as Manhattan Island or so. So they can see each other in the sky in a certain way. They'd be very, very, very bright in X-rays. And they were able to determine that the masses of each of these pulsars was about 1 and 1.4 times the mass of the sun. What they then showed was that the pulsars' orbit around each other was gradually contracting. And as they showed that it was gradually contracting, that meant the period of the pulsars were shifting. And as they shifted, the periodic shift accumulated and accumulated. So what they found is that the pulsar timing, when they got the actual pulses from it, was getting closer and closer and closer together. And that's as a result of the two pulsars approaching each other. So why do they approach each other? Because they emit gravitational waves. So this graph is showing you the cumulative period shift of the orbit of the two pulsars as a function of time. And it takes years to watch it. And each of those red dots is a data point. The blue line that fits them is the prediction of general relativity if they're emitting gravitational waves. And that's how they're losing energy such that they're coming together. And notice how the prediction of gravitational wave emission exactly matches the dots of the data. So that's what earned them the Nobel Prize in 1993, was the implicit discovery that gravitational waves were being emitted by this pair of neutron stars. Well, they're very far apart, 60 Earth diameters apart, so it's going to take them 1 billion or so years in order for them to fall together. And so we won't see them collide or anything, but it just shows that there are two pulsars that can be in very close proximity to each other, less than the diameter of the sun, and that they are apparently emitting, or at least they are emitting gravitational waves, but no gravitational wave detector had been built yet in 1974, nor had one been built by the time that they earned the Nobel Prize. It just showed that gravitational waves were the best explanation for the change in the period of the orbit of these two binaries, these two pulsars. Okay, so with that in mind, people were saying, wow, this is really great. There must be lots more of these things. So what happens when these two things collide? So there was a huge number of studies of pulsars. It's an active area of research of neutron stars and pulsars. And this radio telescope, which is the Lovell telescope at Jodrell Bank Observatory, which is in Cheshire in northwest England, it was in 1957 when they first built it. It was the largest steerable radio telescope in the world at 250 feet in diameter. Now, Arecibo is not steerable. This is an enormous thing that's is 76 meters in diameter. So it's almost the width of a football field, an American football field. Now, the Green Bank Observatory in West Virginia is a bigger steerable scope, as well as the Effelsberg scope in Germany. But this is a big one. So this is a huge telescope. And it's one of the pulsar workhorses in the world. It's discovered a number of binary pulsars, as well as discovering 100 pulsars on its own. And in September of 2006, they were able to assist in showing a different double pulsar, not the HolesThe pulsar, but a different double pulsar was also emitting gravitational waves. So the action of discovery of pulsars is a major part of radio astronomy. So what's a double pulsar look like? So one of the first known double pulsars opens up like this. Well, the Hulson-Taylor binary, one's a pulsar and the other must be a neutron star, but we can't see it. But this is a double pulsar, and these two double pulsars orbit, and this is a double pulsar. The other one would be a double neutron star with only one pulsar being seen. That's the HolesThe binary. But this is a double pulsar seen by that telescope. So these two pulsars orbit around each other. That was discovered by the Lovell Observatory, and orbit around each other in about 2.5 hours. One of the faster pulsars spins 45 times a second, and the other spins 22 times a second. And as they orbit each other, they found that they too would be emitting gravitational waves in terms of their how they're falling together or getting closer and closer. Now, each of these stars, each of these neutron stars, have much larger masses than our sun, but and these are incredibly large things and very, very, very close together. So how might a double pulsar be formed? So let's look at this, how they might be formed. In the upper left-hand corner, we see a supermassive star exploding in a type 2 supernova. It becomes a neutron star with pulsar activity. Its companion in a close binary is also a massive star, goes through its evolution, and then while it's about to die, it's dumping stuff onto the companion to spin up the other pulsar into a millisecond pulsar. Then it explodes, forming a neutron star, and which is also a pulsar. So the upper left-hand corner shows the evolution over, say, 10 or so million or 20 million years to get those stars from main sequence all the way through red giant phase. And as the second red giant swells up to fill its Roche lobe, it'll dump material through gravitation, because the gravitational balance point dumps things across to the other neutron star. Then they explode, and now you've got a double pulsar. So the right-hand side image shows our current observation of a double pulsar, where we see the beams coming towards us as these two stars rotate on their axes. Their magnetic fields are not coincident with their rotation axis, so we occasionally see these flashes of light from them. And as they orbit each other, they slowly lose energy in gravitational waves until they get close enough to collide, like we see in the lower left. Eventually, this double pulsar will get closer and closer and closer. As they orbit closer together, they will eventually collide in a titanic collision. As we see in the lower left, they'll form either a hypermassive neutron star for just a fraction of a second, and then they will form a gamma ray burst, which is the light that you saw there in these jet-like structures. So the end result of one of these things is either a supermassive or hypermassive neutron star, which will only live for a few seconds before collapsing down into a black hole. So this is what we would call a kilonova. And the lower left-hand image shows what a kilonova looks like, which is a much more power, about 1,000 times more energy than a standard supernova. That's why we call it a kilonova. And these things are also the sources for gamma ray bursts. So we can expect that some gamma ray bursts that we talked about in the previous lecture on gamma ray bursts should be due to colliding neutron stars. And on August 17th of 2017, a gamma ray burst was detected by both the Fermi and INTEGRAL gamma ray observatories in orbit. And just a few seconds prior to their detection, the LIGO Virgo Association, because now the Virgo Gravitational-Wave Observatory was online in Europe. So now they had 3 observatories, unlike the others. The first initial discovery, which is simply by LIGO Hanford in Washington and Louisiana. This is 3 observatories able to confirm all at the same time. And notice the gamma ray bursts occur just a few seconds, less than 2 seconds after the arrival of the last moments of the gravitational waves. So this was the first ever joint observation of a gravitational wave and some form of light. So the Fermi Space Telescope and the Integral Space Telescope both have triggering mechanisms that send information to observatories and observers around the world to go try to figure out what's going on and observe these things in, say, X-ray, optical, infrared, radio, what have you, as fast as you can, if you can. So they send out to massive observatories. Now, the Virgo team had a glitch in Hanford that caused them to be delayed by 27 minutes after their initial detection, but they were able to clean it up and say, oh, the glitch made it difficult to find, but they actually looked at it and said there's a signal inside there, And it was a massive, massive, massive signal that they were able to find. And this began the process of a worldwide effort to observe this event somewhere in the electromagnetic spectrum. This was the thing that was being hunted for, the light or electromagnetic counterpart to a gravitational wave event. So this is one of the landmark days in all of astronomy history, was August 17th, 2017. And that signal looked a lot like this. And so what we see is the gravitational wave signal according to frequency, and so you have all the static, but then there's a signal that goes through the frequencies as a function of time left to right, and the actual event was at time 0 that you see there. But stringing all the way back, this looks like it started about 2 minutes prior where the signal actually could be detected. However, the triggering only happened about 30 seconds prior to it, and the summation of that trigger went out to everyone in the world 27 minutes later because there was a slight glitch at one of the observatories. What's funny is that they compare this signal to say, what is the chance that all that random static that you see in there could actually have just kind of organized itself or randomly positioned itself to make this shape? And they make enormous numbers of statistical studies to determine whether or not this thing is actually is a false positive, meaning that's just static, or whether or not it's a real signal. And so they create a false alarm rate characteristic, and they said that this was the only chance is that 1 in a trillion was the capacity for it to be a false detection. So they didn't think that for 1 in a trillion, that's over time, and that means that they would say this would only happen once in 80,000 years of observing. If they observed with the observatory for 80,000 years, only once would this happen randomly. So they said, well, this is a real signal, and they then scanned their data. They found the signal lasted 30 seconds. All of the other gravitational wave events that occurred last only fractions of a second. So this was incredibly different than all the other signals combined, and because it lasted a lot longer, that means it was much less massive, because more massive things, they change more quickly as they're about to collide. So they were much less massive. The only thing I could think is that they'd caught their first gravitational wave from neutron stars. Since all the other things were more massive and much more quick, just like the first one I showed you, it only lasted a quarter of a second from rising out of the noise into the final chirp at the end. Notice the frequency shows low frequency at the bottom and high frequency at the top. So literally all this would sound like is whoop. That's what it sounds like. It's like a whoop. And this was a merging neutron star because of how long it took and basically the signal itself. All right. So how do they actually know where to go and look for it? So then the race was on to find this thing. So the Fermi Space Telescope could see in an oval, Integral could see in a band, and then LIGO and the two LIGO observatories and the Virgo observatory could see in a banana type shape to hunt it down. And so all those circles that we saw before, those are the possibilities of where it could have been in the sky. So you saw that there's a very small number of objects that it could have been. And they were able to isolate the location in the sky because the Virgo detector in Europe didn't detect anything. Remember, the observatories from the previous lecture showed that you had to actually get a signal by having the gravitational waves pass perpendicular through the detector. The fact that it didn't get signal at all in Virgo meant that the gravitational wave signal did not go at any angle perpendicular. It went flat to the observatory rather than perpendicular in any level. So since it went flat, they were able to reduce the entire field of view to about 30 square degrees, or about 60 times the size of the full moon. And that launched a massive search, and within 12 hours, this galaxy had been seen to have some sort of event happening in it. And this galaxy is NGC 4993. And NGC 4993 is an elliptical galaxy about 130 million light years away. And on the left-hand side is a Hubble Space Telescope image from April 28 of 2017. And on the right is from the SWOPE supernova survey from Santa Cruz, where there's a new bright dot right in there. And this was taken by that observatory at that date within 6 hours of it. And when they saw it, they said, there it is. This was the first optical image of this observatory, of a gravitational wave event. Now that's not gravitational waves we're seeing. We're seeing optical light, visible light that came from something that captured gravitational waves. One of only a handful of galaxies inside the search area for this object. So the SWOPE team was able to compare against other previous Hubble Space Telescope images, and that's when they knew they got it. So what's funny is that apparently the people at Santa Cruz, when they said, it didn't really elicit this huge reaction. Hey, there's something new. It's like, oh, there's a dot there that wasn't there before. Interesting. Because they're hunting for supernovas. And a kilonova is just like that. It's just another little bright dot right next to the galaxy. So what happened was, this was the first detection in visible light, not invisible light, but with optical light of an event, of an object that did this. And this is bright enough that if you had a half-meter class telescope or a 1-meter class telescope, you could easily image this galaxy. In fact, some observatories, such as iTelescope, which is a per-pay amateur class observatory, but it also can be used for research, the larger instruments there could easily have observed this event. So the first light with Hubble Space Telescope, Hubble swung around, and they swung the Hubble Space Telescope around to take a look, and yes, they saw it fading away. Other observatories had seen it within 12 hours. Hubble Space Telescope watched the flare die over the course of 6 days. They looked at it about the 20th or so, 22nd or so, and started watching it over the course of 6 days. You know, they had other things to do, and they couldn't exactly rip it away. But they got the Hubble Space Telescope as soon as they could to see this kilonova event and watch the fading glow of this object. It was also observed in infrared. This is the Spitzer Space Telescope, run by NASA, JPL, Caltech. And the Spitzer Space Telescope also saw the event. They were able to, they were looking specifically in the channels of 3.6 and 4.5 microns, which is much longer than visible light. It's deep in the red, and so they were able to see it in infrared. Also, the Chandra X-ray Observatory, the circles show where it is. In previous on the night, there were also in the previous section, the gravitational wave event itself only showed up later, and so there was a counterpart that occurred a little bit later, not immediately, in X-rays. And furthermore, the Very Large Array in New Mexico, the VLA was swung over there by Greg Hallinan and Kunal Mooney. They went over. They got the little arrow points out the object. The center is the supermassive black hole, the center of that galaxy. But this is the VLA radio image, and that radio image comes from the interaction of the material in the surrounding medium around it. So this is also part of their work. And so when they were this was part of a high-speed alert that they actually working with too. And the Australia Telescope Compact Array, or ATCA, also detected it on September 5. So VLA and radio observations occurred too. And here we can see a little summary plot of it with a Hubble Space Telescope image. We can see the Swift Ultraviolet Observatory taking ultraviolet pictures of it. Gemini South is, instead of Spitzer now, looking in the infrared, and the VLA on the right. So this was observed by many, many, many groups. So what did this look like if you happen to have been close up? A merging pair of neutron stars. First, it would take about their merge took about 2 minutes, but the last merge of it took fractions of a second. And there it was, they merged together, and as they exploded, they emitted the gravitational waves. and a huge burst of gamma rays came out and material flowed out from them in the cosmos. The gamma ray bursted material then intersected with the interstellar medium to form the gamma ray burst that we've seen in other objects. This particular thing was, as they plowed through together, the amount of material that was turned into mass was about less than a quarter of a solar mass. And so we see that when neutron stars make the collisions, we're just summarizing it here. The upper right-hand corner shows the collision of the two neutron stars, and as they collide, they form gravitational waves, which are kind of the shimmering, ghostly rings that you see coming out. Those are the gravitational waves. They come directly from the interaction, the collision of them. So it probes general relativity in the very, very, very strong region of where things are going crazy in gravity. But then the light comes later in a couple seconds later as those jets are formed, and then we see the jet on the upper right hand and the lower right, and that as the material slams into the interstellar medium around it, that shocking of the material heats the material such that it glows in gamma rays, and that's the source of the gamma ray light. And we talked about that in gamma ray bursts in the gamma ray burst lecture, as we see in the upper left hand image that comes from that lecture. But most interestingly enough is the lower right image. It's all the debris that came out from this collision, because it probably formed a black hole, but not all of it went into the black hole. The total amount of material that went into becoming the black hole was kind of minimal. So the merging of it converted about a quarter of a solar mass into gravitational waves, and but the important thing is that material that came out that didn't fall into the black hole created huge amounts of heavy atomic nuclei. In fact, it was estimated and then subsequently seen in the spectrum of this kilonova, because so many telescopes and observatories could actually take a spectrum of this light from a distance of only 130 million light years, that it was determined that approximately 16,000 times the mass of the Earth in heavy elements was formed, which is wild. And approximately 10 Earth masses of gold and platinum were formed at that time. So just think like 10 Earths of gold and platinum were made in that moment of collision. So this is very interesting, because this has been shown in terms of the follow-up by the Chandra X-ray Observatory, because heavy elements like these will emit X-rays, or at least the products that would radioactively decay to them will emit X-rays, because they're coming off in that explosion. That kilonova event strongly excites the nuclei, as well as creates radioactive elements that would then decay to these heavy nuclei, such as gold and platinum. So there's a lot of X-rays that come, in this spectrum on X-rays determines what the material is. So that's how we know that there was a huge amount of gold and platinum that was made there. In fact, this provides direct observational support for an incredibly important element of the Big Bang. The Big Bang produced the hydrogen and helium of the cosmos. Stars such as massive stars like Betelgeuse and Arcturus, supermassive type 1 supernovae, such that would have formed the pulsars in the first place, those would give us like oxygen and aluminum and phosphorus and argon and iron and nickel and cobalt and all other things like that, up to krypton or so. But those things would create and push out the iron. But the very heaviest elements the mechanism that was understood to be creating them would not have been an exploding white dwarf, would not have been an exploding supermassive star, it would have to be the destruction of neutron stars. So if you have two neutron stars merging, they seem to be creating most of the heavy elements, and that's the color yellow in this particular periodic table set that we're looking at. They would be creating most of the heavy elements, including all of the iodine, all of the platinum, and nearly all of the gold in the entire universe. So all of the gold that you've ever encountered was created inside as a result of two colliding neutron stars, and this is observational evidence for that. This is the first observational evidence for it. It was theorized up until this point, but now we know that it's actually occurring. That's just an amazing, amazing thing, and that was discovered by the event that happened on August 17th of 2017, the first observation of two neutron stars colliding, both in gravitational waves as well as in electromagnetic spectrum, all across the spectrum. One of the most studied transient phenomena in the history of astronomy happened in that day. Well, what this means is that there's a lot more to see of all of the gravitational wave events. And so here's a little slide that shows the ones that have been seen. You can see there's 5 events that have been seen by the LIGO-Virgo collaboration, and there's 5 black hole mergers where the 2 black holes collide. Now they don't make heavy elements. Why? Because black holes are already inside their event horizon, so nothing gets out. So the black holes simply collide. They don't make a hypernova type explosion. They don't make a kilonova type explosion. They just make a gravitational wave event. However, neutron stars make a lot of light because their physical structures are still objects of extreme density, so to rip them apart it will create a huge amount of debris and a gamma ray burst. So now that we know that gamma ray bursts come from 2 neutron stars colliding. We do know that. We also know they come from hypermassive stars collapsing. But this was the most studied, as we can see, of all the neutron stars that have been seen by LIGO and Virgo. The LIGO-Virgo combination actually showed the first one ever. And hopefully there will be many more to come as they've taken the system offline to do some upgrades, and because it's a huge undertaking actually to do this. And so only 6 have been found so far as of the fall of 2018. And hopefully there will be more in the future, because this is the future of astronomy, is gravitational wave observing, which involves enormous collaborations, extraordinary commitment, and then commitment between particle physicists, engineers on the ground, and astronomers looking with multiple different kinds of telescopes. So this incredible thing can then be summarized. They have a cool little fact sheet. I'll kind of zip through it because this is really neat. All sorts of stuff. There's some factoidal things. And finally, there's some websites for you to go take a look at because, heck, that's what they're all about. The LIGO Observatory, as well as the Virgo Observatory, and this is one of the most important things that happened in 21st century physics. Thanks again, and we'll see you soon.